Okay, good afternoon everyone. I think I should probably start doing this. It's roughly 1:30, so may as well get going. This is BGP multi-homing techniques tutorial. Those of you who have been to NANOGs before know that we try and do BGP tutorials at each NANOG. This is one of 3 different varieties that we've had here in recent years. Those of you who came to Arizona will probably remember the intro to BGP that was presented there. And for the next NANOG in Chicago, we'll be doing BGP troubleshooting, which, before I start, is worth mentioning. For the troubleshooting tutorial, if anybody is interested in helping out with that, i.e. from the operator community, because it's all nice and cool having vendors standing up here telling you how to do troubleshooting, but it's actually a lot more useful to hear about how operators will do troubleshooting within their own networks, especially dealing with some of the stranger BGP issues that you normally face. I know that a lot of the operators are doing pretty serious troubleshooting work because I work with them a lot, but I can only present the techniques that I'm aware of and I see that people use. And then from my days at UUNet, I know that we did a lot more weird stuff than I can possibly present up here. So, what this is going to be all about, I've got lots and lots of configuration examples in this. Because I work for Cisco, well, that's what I know. All the config examples use Cisco iOS command line interface. Apologies to those of you who have never ever seen that sort of CLI before. I hope it is reasonably intuitive that you can translate it into your own brand of CLI. I've aimed this one at service providers, funnily enough, because this is NANOG, it is an operator meeting, but a lot of the techniques can actually be used for enterprise networks as well. Certainly enterprises connecting to service provider backbones and so forth. Feel free to ask questions at any time. I don't mind interruptions. If you want to keep the questions to the break, that's fine as well. Or any time during the week, or simply drop me an email. You can do that also. Presentation slides, you can get those from 2 places. On the FTPN site at Cisco that I've listed there. And they have just been posted onto the NANOG website as well. They weren't there about 10-15 minutes ago, but Susan tells me they are there now, so if you want to download the slides, you can do so. This is the only microphone I've got, so I can't wander about too much from my pedestal up here, so apologies for that. I'll just stand here and look, well, whatever, speech presenting like sort of person. Okay. I've got a lot of material here, far too much for the 3 hours that I've got. That's always what happens with these sort of presentations. You hear new good things that people are doing, so you add them into the slides. Well, this presentation is now about 230 slides. It's far too much for 180 minutes, so I will skip a lot. I will skip the configurations by and large. Once I've explained how the first few work, I don't think there's much point laboring through the rest of them, but I'll spend more time discussing some of the particular configuration options rather than the actual CLI itself. Okay, so first point, why do we multi-home at all? What's the point? Why is there such a fuss about it? Why do people want to do this? Well, multi-homing is all about redundancy, diversity, and reliability, and that's basically the reasons why end sites who connect to the internet are really interested in multi-homing. The first one is redundancy. If you've got one connection to the internet, well, it means your network is dependent on your local router, its configuration, software, hardware, operators, all the local environmental things like that. It's dependent on the WAN media, in other words, how you connect to your upstream service provider. So it could be physical failure, could be carrier failure, something going wrong in upstream network, something going wrong in the actual physical network connecting you to your upstream service provider. cables being dug up, cables being broken, all kinds of things like that. And it could also be dependent on your upstream service provider. So their configuration, their software, their hardware, network outages, maintenance, all this type of thing. People like to have redundancy. Even though you've sold the 100% reliable router, the 100% reliable networking equipment, the 100% perfect fiber optic connecting you to your service provider, well, you know in real life that just doesn't happen. So people, if they've got mission critical business or whatever they're doing on the net, they tend to want to make absolutely sure that this connection will not ever break. Reliability, well, that's really what I was leading on to. Business critical applications demand continuous availability. If you look at some of the major websites on the internet, they connect to multiple service providers through multiple paths in multiple locations. They simply cannot afford for one location their only link to go down. They're out of business and the time costs money. Supplier diversity. Many businesses are demanding supplier diversity as a matter of course. An internet connection with 2 or more suppliers then gives you 2 or more diverse WAN paths, 2 or more exit points, 2 or more international connections, 2 of everything pretty much. And one thing that, well, you find a lot of people talking about the internet, and certainly I've gone on and on about it for the last 5 years or so since I've worked for a vendor. 2 of everything is critically important for most internet businesses. Bit of background about myself, if you don't know, before I joined Cisco, I used to work at UUNet. And one of our major service offerings was, of course, the capability for customers to multi-home, explain to customers how important the internet was, and having a really, really redundant and super diverse network. I mean, that was how we built our network within the UK and within Europe. The US operation was exactly the same. It was super redundant. You could knock out parts of the network and the rest of it would still work. Having the super reliable network meant that customers who connected had a super reliable connection. And of course, customers realized that we were doing this and they wanted the same thing for themselves. So this is where all the multi-homing thing came in. This is the other reason. You know, I live in Australia. I spend most of my working life in Asia Pacific, sometimes coming to North America, sometimes going to Europe as well, and even going to Africa, which is what I'm going to be doing after NANOG finishes. The other reason, leverage. Playing one ISP off against another one. Quite often where one ISP is probably not really very good, it may be your first supplier, and you're fed up with them, annoyed and all the rest. You multi-home to improve the quality of service. You don't just chop off the connection and go through all the hassle of getting another ISP, you go connect to another one. So you have 2 connections, and then you can play one ISP off against another. Now when I was in operator land, I really hated this. It meant that I was losing potential revenue to my competition. And I really didn't like being played off against another ISP because, for all the reasons that I've gone through before, we thought we had a really, really good network and it was better than everybody else's. But I see it quite often in my work. End sites will multi-home so that they can play off one ISP against another for service quality, in other words, the reliability of the connection, service offerings even. One ISP may only offer a certain bandwidth of connection, another ISP may offer 5 times that bandwidth, so the customer will go to this other service provider, say, oh, I get a bigger connection, forcing the other one to do something if he doesn't want to lose the revenue. And of course, the magical availability. Okay, so multi-homing is easy to demand as a requirement of any operation. You see that a lot in other walks of life. Redundancy is quite important. Having more than a single connection to your supply is actually really important. But what does it mean in real life? What does it mean for the network and for the internet? And most importantly, how do we do it? Having a static single point connection to the net is really easy. Multi-homing brings you into the wonderful world of BGP and so forth. So, some of the definitions and options. In other words, what does it mean and how do we go about trying to do this? Multihoming, this is my definition, this is my engineering definition. People debate what multihoming means on umpteen mailing lists, and well, yes, I probably should be interested, but quite frankly, I'm not. Multihoming is quite simply, you have more than one link external to the local network, whether it's 2 or more links to the same ISP, or 2 or more links to different ISPs. Notice the second point, usually 2 external facing routers. If you've only got one router for your external facing connections, you've only got provider redundancy. You don't have router redundancy. And quite frankly, I think you're wasting your time, even multi-homing, if you've only got one router. I mean, I've been around long enough, 12, 13 years in this industry to know that boxes are never 100% reliable. You will also need an autonomous system number. You're going to have to use BGP for your multi-homing. And this is the next panic that people end up going into. AS number, where do I get that from? It's impossible. Well, it's not really. You can get one from your upstream ISP. If your upstream ISP is interested in your business, well, if you got address space from them, you can get an AS number from them. If you're a member of any of the regional registries, and there are 4 of those, APNIC, ARAN, LACNIC, RIPE-NCC, you can get an AS number from them as part of your membership. Getting an AS number is not hard. So an AS number is necessary when you have links to more than one ISP, or you have a link to an exchange point. AS numbers are 16-bit integers. They range from 1 to 65534, 0 and 65535 reserved, and 64512 through 65534 are private AS numbers. Private ASs are used for particular applications. You cannot use private ASs on the internet. Well, you can if you want to, but as with private address space, you won't get anywhere at all. They will be filtered by your neighboring or upstream ISPs. But you can use private ASs for many applications, such as if you're an ISP with customers who are multi-homed onto your backbone, as described in RFC 2270. Or you can be a corporate network with several regions, but you only connect to the internet in your core. That happens quite a lot also. And of course, within a BGP confederation. If you're using BGP confederation to scale your internal BGP, then you would use private AS numbers for that as well. So those are the 3 areas you'd use private ASs. I mean, you could use a private AS in your lab and any other parts of your internal network where you wouldn't need to connect to the real live internet. Private ASs must be removed from all prefixes announced to the public internet. So include a configuration to do this in your eBGP template. As with the private address space, RFC 1918 address space, private ASs are intended for internal use in the network. They should not be leaked to the public internet. And those of you who watch, the ARAN's RTMA mailing list, you'll know that I send a weekly routing report to that, or some of you will know the CIDR report. Both of those will point out private ASs that are being announced to the internet, and which networks are sending these private ASs, and so forth. And people will come chasing you. Some people pay attention to the CIDR report or my routing report, and they will send you emails saying, why are you doing this? And it's usually just a misconfiguration where someone has forgotten to put in the specific remove private AS command, or they simply didn't know that these were private ASs even. Okay. To configure it, well, the Cisco iOS example is there. It's similar on Junos. Remove private AS. Make sure that's part of all your eBGP configuration. Now, configuring policy. I've tried in all these examples to keep things simple. One of the things I've really found that makes BGP easy for people is to try and keep things simple. So what I'm going to do is use prefix lists to filter prefixes, filter lists to filter on AS path, and route maps to apply policy. Now these are iOS specific. Again, if you're not using iOS, you have a similar concept for your own equipment. Try and parcel them or pigeonhole them properly. Route maps can often be used for filtering as well. And I find a lot of people they read the manual and they discover that route maps can be used for all sorts of wonderful things. And they try and do all the wonderful things as they're learning BGP, learning multi-homing configuration. Please try not to do this. Get experience first, and then if you really find you have to, use the route maps for more than just applying policies. BGP's policy tools are these. You've got local preference for determining outbound traffic flows. If you remember, those of you who came to the last BGP tutorial, local preference you apply to what you hear coming from your neighbor. So that determines outbound traffic flow. MED works in the other direction. It determines how traffic flows into your network between you and your neighboring ISP in the event of you having several interconnections. AS-path prepend is what does the same thing, but it has internet scope. MED only works between you and your neighboring provider, whereas AS-path prepending has internet visibility, global visibility. And of course, the most important tool of all, community. The BGP community lets you do a lot of really specific inter-provider peering policies. The tail end of this presentation has lots and lots of examples of how ISPs are using communities for multi-homing and other purposes. Now, originating prefixes, well, I'm going to make assumptions. And the first one is you must announce the signed address block to the internet. If you're a member of a registry, you will get an address block from the registry. You will not get Class Cs or Class Bs or Class As, but a large proportion of the world still believes that the internet is classful. Classful, remember, disappeared in 1994, 9 years ago. So we think this is probably historical now. So when you get your address block from the registry, announce this always. Yes, any address space the registries hand out is not guaranteed to be routable, but at least it's going to be more routable than chopping your address block into Class C size chunks, in other words, /24s. I've also said you may announce sub-prefixes, but the reachability of these is not guaranteed. Okay, you may only get as far as your neighboring provider, or you may only get 2 or 3 providers further. If you're really lucky, you might get internet visibility. Now, the current RIR minimum allocation is a /20. I think all 4 RIRs have that. Several ISPs will filter the RIR blocks on this boundary. Several ISPs will filter the rest of address space according to the IANA assignments. I've heard some people call this net police activity. I mean, there isn't really any net police as such at all, but several ISPs have decided that, well, this is the registry's minimum allocation, therefore that's all I should see and that's all I need to see. Because an ISP will only ever get this block. They should never be sending anything smaller. So I don't need to see it. It's not giving me useful information. Now, the regional registries do publish the minimum allocation sizes, or at least the 3 original do. I can't find any reference on LACNIC's website about what the allocation sizes are, but I imagine they'll be no different from ARAM. But they are all there. So if you want to try and figure out what could be routed or what could be filtered by some ISPs, there you can find it. IANA publishes the address space it has assigned and allocated to the RIRs. So that's listed there. And several ISPs will use this information to construct BGP filters. I mean, you've seen the huge debate on the NANOG list over the last month or 2 about network 69/8. Well, see, some ISPs have gone and taken 69/8 and said, oh, well, it's not used by anybody. But of course, now that it actually has been allocated to registry, people aren't keeping these filters up to date, and we have the routing problem. If you're going to do filtering based on this type of minimum allocation size, you need to be on the ball all the time. Now, Rob Thomas, as a service to the community, posts to the NANOG list and every single operator list that I know of about when a new block is handed out to the registries. It's really important to pay attention to this, especially if you're doing this sort of filtering, because it just breaks connectivity for so many providers, or so many end sites. Okay, The original intention, I suppose, was to punish ISPs who pollute the routing tables with specifics rather than announcing aggregates, which could well be okay in North America, but the internet is a lot more than just North America. As I say, I do a lot of work in Asia Pacific and more recently in Africa, and well, these guys do suffer big time with some of the net police filtering, because the fact of life is, with the satellite connectivity they have to have, they get the @/20 from APNIC, but it's only 1/20. How do you load share over 5 or 6 satellite connections with a single /20? The only way you can do it is subdivide. There is nothing else you can do. So it does impact legitimate multi-homing on the edge of the internet. And regions where the domestic backbone costs a fortune compared with international bandwidth. I mean, that is true in many countries as well. It's hard to maintain, as I was saying. Pay attention to Rob Thomas's posting. Pay attention to the registry's email that they send to the operators list. I mean, there's enough information out there saying, this block has now gone to such and such a registry. There's no real excuse for anybody keeping legacy filters in there. So the important last point, don't do it unless you understand the consequences and you're prepared to keep the list current. Many ISPs do, but there are many others who, maybe it's somebody 3 years ago configured this and got made redundant in the current climate, or left because he got tired out or burnt out, and the new people have no idea that this is in place and they don't understand how it works and are afraid to touch. I mean, that happens too. So be aware of it. Hopefully this tutorial will make you aware, and if you're new to your network operation and you're not quite sure what's going on, you have been afraid to touch, hopefully you'll be a bit more confident to touch at the end of this. Okay, the scenarios that you can get. Well, we can get a stub network. I've often seen people say, well, this is multi-homing. It's not really. You've got 2 parallel wires between your router and your upstream's router. Okay? This could be like 2 T1s, and you're really using 2 T1s to give you effective 3 megabits of bandwidth. It's not really multi-homing. Don't use BGP. You don't need to. You can if you want, but there's no real need. Simply point a static default at your upstream, they point a static default at you, and the router just load shares quite happily by itself.
Is there any reason to do that? I mean, is there a reason other than BGP that getting the AS announced out to the internet so that when people are tracking problems, they can see whether you're announcing it or not? I've seen people go back and forth in this argument about whether you do a static if you have an AS.
I mean,
part of the community somehow.
If you have your own public AS, then you could use your AS for there. And the thing is, it's not giving any more information to the internet. But if you have one, use it. But I've seen a lot of people who will approach the registries or enlist my help. Oh, can you go to APNIC? I want an AS because I'm doing this. And I can't. It's certainly in APNIC's rules that you don't get an AS for this sort of thing. But I mean, if you have your own AS, or if you want to use a private AS and your upstream's quite happy with doing it, as you see in examples a little bit later on, you can use something called eBGP multi-hop there to do the load sharing for you. That's quite possible as well. I wouldn't say there's a right or a wrong. It's just if you're coming new into it and you've got this situation, you're not going to get a public AS number for it. If you've got a multi-home stub network, in other words, where you've got your router and your network connecting to different points of presence in your upstream ISP, then you should use BGP for this. I mean, this was one of my favorite services when I was working for UUNet. It meant that we didn't lose customers to competition. We would connect them to different points of presence in our backbone, and they multi-home to our network. And we would challenge the customer to prove that they actually couldn't get 100% connectivity from us. And as far as I remember, nobody ever managed to prove that both connections broke. So this was actually a really good service to offer. But yes, use BGP for this. Static routes, you don't get any control. And please, for goodness sake, don't use an internal routing protocol. I've seen people use OSPF for this. And it interferes with the OSPF that the customer runs, or it interferes with the OSPF in their own network. And it's just messy, it's ugly, and it's basically a don't do. IGP means internal routing protocol, right? Internal is inside your AS number. It's not between AS numbers, right? So don't use OSPF for this. You can try it if you want to, if you don't believe me, but I've done this often enough. I've broken enough networks myself doing this. I had to fix enough broken networks myself doing this, so no, just don't. But you won't get a public AS number. Use a private AS. There are plenty of them, 1,023, so use a private AS number. It works just fine. You can use all the BGP you want. You can go. Okay? It's a sign. Thank goodness it's a sign. I was thinking I'm about to disappear through the floor. That's what it felt like. Okay, yes, use a private AS number for this. Again, you won't get a public AS. You can use all the BGP you want. You can do all the load sharing, all the rest. It works just perfectly. This one, you will need a public AS. This is a fairly complex situation. It's very common in the internet today. Your network AS100, you connect to 2 or 3 or more, however many upstream ISPs. It's a complex thing, multiple circuits. You need to do load sharing, traffic engineering, all the rest. So that's pretty complex. And that's really what the gist of the whole of the rest of the presentation will be about. Now, here's some examples before we plunge into the main thing. If you've got multiple sessions to one ISP, rather than using the static route thing that I was pointing out a few slides ago, you can use something called eBGP multi-hop. And this is where your router and your AS will talk eBGP to the router in the upstream ISP, there in AS200. And you're using BGP to load share, in this case, over 3 parallel paths. Right? The BGP session runs between the loopback interfaces of the routers in each AS. And this is a very good way of load sharing. This is most commonly used in service providers who have probably a real AS number. They've got multiple circuits running between the ASs, and they're talking BGP between the neighboring networks. Okay, so that's one way of doing it. I've thrown in the Cisco configuration there for your interest. Again, hopefully you can translate that into your favorite vendor if you need. But try and avoid using eBGP multi-hop unless it is absolutely necessary, or you're load sharing across multiple links. The other case you can use eBGP multi-hop, and it's the most common one, is if you're providing, say, a BGP feed for a route view type service. So for example, the route views facility at the University of Oregon, or the Oregon IX. That's spawned by eBGP multi-hops from lots of service providers around the world. The CIDR report, again, gets lots of BGP multi-hop feeds, and that's generally the way you try and use it. I see lots of ISPs who just use eBGP multi-hop because, and I'm like, well, that's okay if you know what you're doing and you're prepared to put up with your customer not really understanding what's going on. I've seen so many breakages with people using eBGP multi-hop, and I actually got this one from one of the big ISPs here in the US, and that was, they said, we will run eBGP multi-hop, but do not support it as a standard offering because customers generally have a hard time managing it due to routing loops and fail to realize that BGP session stability problems are due to connectivity problems between the CPE and the BGP speaker. Yes, question?
So just to clarify, you're not discouraging the use of eBGP multi-hop for internet-wide data collection and wrapper collectors. You're discouraging it for production use within an AS as part of peering?
Yes, I'm discouraging it for production use between ASs for peering. For data collection, it's the only way you can do it.
Right.
Yeah.
Exactly.
But for peering between you and immediately neighboring AS, really discourage it. I mean, some ISPs do it and they're happy with it and the customers are happy with it. And I'm not saying they're wrong or anything like that. But for people who are thinking about doing this, try not to do it until you really understand what problems it can lead. I've seen people get this wrong where you need a static route for the point-to-point link to tell your router where the remote is. What if these links go down? You get the static route wrong. I've seen eBGP multi-hop sessions go around the world rather than sitting on the immediate point-to-point link. And the customer is completely oblivious apart from seeing horrendous round-trip times. and then blaming us for the internet being slow. Okay? And that was the bit that I didn't like. So it was like, we're not going to do this because the customer doesn't understand what's going wrong. Blames us for what's basically their misconfiguration. So if you're happy with it and your customer's happy with it and they can sign this sort of saying, yes, I'll fix any problems caused by using it, then fair enough, but otherwise, no. Okay, the second example, you can use something called BGP multipath. Again, this is, I suppose, the same idea to the eBGP multi-hop, but in this case, you're setting up 3 BGP sessions between you and your neighboring AS. Again, the idea of this is to do load sharing. iOS has got a limit of 6 parallel paths. Junos, I think, is 8 or 16, depending on which internet processor you're using. But I suppose the downside of this is you need 3 BGP sessions, and, well, with the full routing table, do you really want 3 BGP sessions with the full routing table and everything that means? Probably not. So this has a limited use in certain situations as well. But this is another way where you can do load sharing on parallel circuits between 2 ASs. It's not strictly multi-homing, but you can use BGP for this type of thing. If you've got multiple sessions to an ISP, and this is the sort of picture that I'd like to see in most networks, where you have redundant routers in your AS, redundant routers in your upstream, well, the simplest scheme is always to start with defaults. The sad thing about people who start off with BGP is they want it to be really, really complex. And it's like, why? BGP is actually very, very simple. And start off with the defaults. Start at the bottom and work upwards. Build in complexity. Don't download some horrendously complex BGP configuration that worked for somebody and try and doctor it for your own use. Start simple and build up the complexity. And then you'll find that BGP is actually really simple. Okay, so simplest scheme, use defaults, learn advertised prefixes for better control. You need some planning, you need to monitor it, and you need to do a little bit of work. But you will achieve load sharing doing this quite easily. There isn't any magic solution. I mean, it'd be great if there's just a one-line configuration in the command that was, router BGP, whatever, BGP load sharing, and it just did it. But unfortunately, there's not. There are several companies who will sell you services that will let you work on how your BGP load sharing configuration is, but there's no such thing within the router, as you can probably understand. Okay, we'll now move on to connecting to the same ISP, the next section. Now this is the sort of multi-homing where you're going to use a private AS. It's a simple case of multi-homing. Your ISP is offering great deals for your second or third connection to their network and to the internet, so you go with 2 or 3 connections to them. And the case of how do we go about trying to configure these? Well, as I said before, we use BGP for this type of multi-homing. We use a private AS. You won't get a public AS from the registries for it. There's absolutely no justification whatsoever. Because making the network to the end site visible gives no useful information to the internet. You're connecting to the same upstream. So the upstream is part of his address block. That all gets announced to the net anyway. Why announcing pieces of the upstream's net block to the internet is any use, I'm not sure. Okay? There's no useful benefit for doing this. The upstream ISP does what's called proxy aggregation. He's announcing his aggregate to the internet. Your address space comes from his aggregate block, so he just announces aggregate block as normal. If you've got your own address space, then he simply announces your address space as though it was part of his. So that works also. So again, starting from the principle of nothing at all, we're going to build all these from the ground up. We're not going to start with complex configurations. Let's look at, well, the first case, where you've got one link as the primary link, another link is reserved simply as the backup. This one could apply when an end site has bought a large primary WAN link to the upstream ISP and a small secondary WAN link as a backup. For example, it could be a T1 circuit that they're choosing to back up with a 56K. Now I agree it probably doesn't make much sense trying to do any of this these days. 56K is simply not going to take the capacity that a T1 can offer. But I've seen a lot of people who just want any sort of connection to back up the main link. And this is how we might go about trying to configure it. So it could be a picture like this. The link between A and C is the primary link. Between B and D is the backup. We're using a private AS number. And router E, which connects to the internet, removes the private AS, and it will remove any of the customer sub-prefixes from the internet announcement. How do we do? How do we configure it? Well, we announce our /19 aggregate. Assume that this outside it has a /19 network block. We announce the 19 on each link. Remember I said at the start, we're always going to announce our network block. We're not going to announce this 19 as 32 Class Cs. Number one, because Class Cs don't exist. Number two, well, why do this? Why announce 32 network entities when a single /19 is all yours anyway? Just makes the internet routing table bigger and bigger and bigger. So on the primary link, we announce our /19. And on the backup link, we send out our /19, but with a reduced, hang about, I've got this the wrong way around. Announce our /19 with an increased metric. This is what happens when you try and do slides with jet lag. So I will just fix this. Wonders of PowerPoint. Right. Okay. Outbound, we announce our /19 unaltered on the primary link, and on the backup link, we announce the 19, but with an increased metric. If you remember, lowest metric wins in any metric decision, so if you announce it with an increased metric to the neighboring ISP, then that becomes a less preferred path. Inbound, we receive the default route on the primary path, and on the backup path, we receive a default route again, but we reduce the local preference. Remember, highest local preference wins. So if the default local preference is 100, you get 100 local preference on the primary link, and in the backup link, say your local preference might be 50. So that makes it the backup path. And that way, all the traffic will use the primary link in both directions, and the backup link will not get used until the primary link is failed. That's a simple example. Okay. I've put in the configuration here. I'll skip through it, but that's the configuration that makes this actually work. So I mean, the route array is very simple. We just send our aggregate outbound. We accept the default inbound. And for the router B, which is the backup link router, again, we're sending our aggregate out, we're receiving the default in, and the route maps apply the policy which will set the metrics. So I've set metric 10 outbound, and I've set a local preference of 90 inbound. And that makes this the backup path. And router C for the upstream ISP, well, the beauty of this for the upstream ISP is that they simply do not need to do anything special on the routers. They've left the load sharing to the customer. That's one thing I learned very, very early on at UUNet. If you get involved with trying to do load sharing for customers, they phone you up every other day saying, can you do this? Can you do that? And it becomes a support burden. And of course, you're changing configuration on an aggregation router during the day because usually they want things now. They can't wait for the weekly maintenance that you do in the network. So if you give the customer the tools, tell them what they can change, then you just have a standard configuration on your two aggregation routers, and they start sending the metrics and changing the local preferences. Much better way of doing things. So if you see these two slides, the only thing that changes here is the actual neighbor address. Router E is your border router. U is the ISP, and AS100 is your border router to the internet. And well, you have a very simple configuration there. You're removing the private AS, so 65534, which is part of your standard configuration template. So the 65534 does not appear in the net. And of course, the next line, prefix list customer out. Well, this is the address space that your customer has, 221.10/19. So that makes sure that that address block only gets out to the internet. So the customer is deciding to send lots and lots of /24s, then, well, you're filtering those anyway. So you only send the block to the internet. Private AS, of course, is still visible throughout AS100. So it just looks like any other standard external BGP peer. But as far as the internet's concerned, AS65534 network is just another simple customer of this particular ISP. Of course, that configuration isn't very realistic. Nobody buys two circuits these days and leaves one simply as backup. If you've got two circuits, you want to see traffic on both of them. So this example is more realistic. You've got load sharing on the two circuits. It's a more common case. Now this example, I'm going to assume equal capacity circuits. Say you've bought two T3s or something like that. Okay, it's unusual for people to buy lots of different sizes of circuits. Some places you have to because that's all available. But usually you just buy two equal capacity and then figure out how to multi-home and load share with those two. So you've got something like this between AS65534, again a private AS, and AS100. We're trying to use both links equally. Router E does the same as it did before. It removes the private AS and any customer sub prefixes from the announcement. Well, what do? Again, we announce the /19 aggregate on each link. We're assuming the end side has got a /19 block. We announce it on each link. We carry on announcing this. Now, to try and do a load sharing, we're going to take the 19 and subdivide it into two 20s. So we're going to announce the 19 on each link, and then we're going to announce the two 20s as well. The first link is going to get the first /20, the second link is going to get the second /20. And that gives you basic inbound load sharing. It assumes that each host in the customer network is generating the same amount of traffic and drawing the same amount of inbound traffic. Now, I agree that is completely unrealistic. But the principle that I'm trying to get over in this tutorial is start with something simple. If you start with something simple, so I'm doing the basic subdivision. We're going to try this, see how it goes. If it gives me what I want, then fine. If it doesn't, then we're going to refine it a little bit more. Okay? We vary the split until we get perfect inbound load sharing. Now, it may be out of this address space only, say, the first /23 is being used. So you need to do the refinement to try and load share between these two /23s, which may mean that you're announcing a single 24 out one path and a 24 out the other path. So what? It's between you and your upstream ISP. The internet is not going to see this detail. What about what we hear from the upstream ISP? We accept the default route. We only need to hear the default. If you look at most end sites, well, most people in most networks are using web browsers. They're downloading information from the internet. So traffic flow between the internet, well, the ratio between the internet and an end site tends to be about 80% inbound, 20% outbound. So you really don't care which way your traffic is going out. So accepting a default from the upstream is more than sufficient. Just use a simple nearest exit routing, and that usually does fine. Again, I've got the configurations. So you can see I've got the 19 and I've got the first /20 there. So I've done this particular subdivision. And router B was a similar thing with other /20. Router C, of course, well, the configuration changed. There's only one line that's different from the previous example. And now I'm allowing my customer to send me a 19 and a 20. In fact, when I looked at an ISP who was actually doing this fairly recently, he allowed the customer address block all the way down to about /25 or 26. Okay? He basically didn't want to get involved in this customer load sharing. So he just set up a prefix list that allowed a customer to send all prefix sizes from his address block size all the way down to, well, as small as the customer wanted to go. And the customer would send all this into his own backbone, and of course, going out to the internet, we still filtered, so only the address block made it out. Okay, so this way, router C, router D is the same thing. You don't get involved in your customer load sharing. You send them the default, and you give them the tools to fix up their own load sharing. Yeah.
This ends up getting pretty maintenance intensive over time as traffic patterns change and as addresses are allocated, doesn't it?
Getting maintenance intensive over time, well, it depends. I mean, when I was doing this sort of thing in my day, we left all this stuff to the customer. We just had this configuration.
Sorry, I meant maintenance intensive for the customer.
It's maintenance intensive for the customer, yes.
Right. I
But
understand that you're passing that up.
yeah.
Just identifying there's bugs
So,
there.
see, some customers don't want to do this work, and of course, our salespeople love that because then they could go sell consulting services. Other ISPs, other customers wanted to learn about BGP, or they fancied they knew about BGP. So we were like, okay, here you go. Go play. If you break it, it's your fault. And then we can charge you money to fix it. I know it's all sort of around the nasty money thing, but we found this was actually good for us as well. I mean, we could do this. It was a nice, simple configuration for us. We could give the customers a simple thing that they could start with, and they could go play with it. And it was up to them, really. If something broke, they broke it. And of course, they would have to take the flak from the management people. We couldn't be blamed. So it made sense as well from an operational perspective. Our NOC didn't have to get involved, the support people didn't have to get involved, the sales people didn't have to get upset at the engineering people for complex configurations. So if you think through all the things like that, this actually makes a lot of sense. And of course, the other thing is, you avoid having specific configurations for customers. If you're writing up a particular configuration for every customer you configure, then you have an unmanageable mess within your own configuration. And any ISP running a network like this, you want to use configuration templates for everything. And that was the customer template. It was very, very easy. And we could give it to our installation engineers and say, this is the template, plug the numbers in, configure it, and it will work. And of course, they were then going configuring BGP on the aggregation box with just this. And we didn't have to be afraid that they might break something. Okay, so load sharing configuration is only in the customer router. Upstream simply has to remove the sub-prefixes and remove the private AS. For this one, we could also use BGP communities. I mean, we'll see that much, much later on. Right, RFC 2270. 2270, I suppose, is the refinement of the previous two examples. This was written up, I think this is what MCI used for their multi-homed customers a few years ago. And as I point out, it's unusual for an ISP to have just one dual-homed customer. This is a wonderful service to offer because it means you can have customers multi-homed onto your own backbone rather than multi-homing between you and another provider. Okay? I always think it's better for an ISP to have a customer multi-home on my own network than with another provider. But nowadays I'm thinking about it from the size of the internet routing table point of view, whereas 5 years ago I was thinking about it as, well, I'm losing a customer because as soon as he multi-homes, then there's a chance that he can cancel the circuit with us altogether. So give them two connections and they're generally pretty happy. So we look at scaling the configuration. You don't want custom configs per customer, so you scale the configuration, which means you simplify things. We're using templates. You can use things like BGP peer groups and so forth. And every customer basically has the same configuration. So that's a picture. Lots and lots of customers. They can all use the same AS number. And there's no BGP loop detection problem because you're only ever sending a default route to your customers. So there's no big issue there. Router E still does all the aggregation and removing private AS as it did before. So that's nice and simple. Everything is pretty much the same. Router A and Router B configuration, you've written up your template, you simply give it to your customer. So when you connect a new multi-home customer up, dear Mr. Customer, here's the template. Go fill in the addresses, and off you go. I mean, we actually got as far as producing a configuration that was everything ready. All we had to do was cut and paste it into the router. Address space isn't overlapping, so there's not a problem trying to do this. We can use the same private AS. It's all quite easy. The configuration we'll give to a customer could be something like that. Again, we announce the customer address block, and then we subdivide the address block in any way we like. So here I've announced the 19 as well as the 20, or you can cook it whichever way you wish. The win comes on the aggregation router, though. And here, the router C is the aggregation router. I've now can set up a peer group with my private AS in it. The default originate goes in there, and the prefix list default out. So I can put all that in my peer group, and then I just apply the peer group to each and every customer. Inbound filtering, of course, is still different for each customer, which is fair enough. But outbound, which is what the peer group applies for, is one configuration. It keeps it all simple. So when I add a new ISP, a new customer, I'm simply adding those 3 lines at the top plus what the prefix list is for the network block. And this makes it really, really easy to do. I could trust the installation folks to go and do this, even though they knew nothing about BGP. The router E configuration, well, if the customer address space all came from my address block, then, well, it got very, very simple. But if the customer came with their own address space, then we could just build something like this on the border router that connects to the rest of the net. We removed the private AS, and then we just had a prefix list with all our customer address space sitting in there. Or we could use communities for this also. The customer prefixes come from the ISP address block. Of course, do not announce them to the internet. Right? We've got enough internet pollution address space at the moment, so don't announce them. There's no need. You don't add any extra information. So you do something like this. Prefix list, my aggregate out. So in this case, the address space all came out of 221.8/13 network. Then you could just simply announce it like that. You don't even need the remove private AS command, because the private AS is only associated with sub-prefixes of that network block. Of course, if you're more like me, you'd be super safe. You'd put the remove private AS in anyway, just in case your prefix list somehow got blown away. Okay, where are we with time? Okay, doing fine. Now, the next bit, this is probably more relevant, more pertinent. I think multi-homing to the same ISP is probably less common than multi-homing to different ISPs, which is what most people are trying to struggle with these days. Well, here we need to use a public AS number. You can use a private AS if you want to, and you can agree it with the other ISP. And this does happen. Some people don't like seeing inconsistent ASs in the routing table, and which is what arises from the use of private AS. But I'll look at that in the next slide. Address space comes from both upstreams, or it can come from the Regional Internet Registry, or it could be historical from IANA, whatever. But the configuration concepts are very similar to what we covered in the previous multi-homing to the same ISP situation. Let's have a look at the inconsistent AS. If you go out into the internet and you're using, say, a private AS to multi-home between 2 different upstream ISPs, if you look at the prefixes originated by that AS, it looks as though they're actually being originated by both AS210 and AS200. And some people get really up in arms about this. Because yes, I suppose if you look at it, well, I wouldn't say naively, but certainly if you look at it innocently, it looks as though 2 different ASs are originating the same address space. So 2 different networks are using the same address space, so maybe one has stolen somebody else's address space or something like that. I mean, that's possible. But the more common situation is something like this. You have a network that's multi-home between 2 service providers or 2 ASs, and they're using a private AS number to do this. Okay, it's not bad, and it's definitely not illegal. And you can do it. There's nothing wrong with doing this at all. And if you look on the internet today, you see about 600 or 700 different networks which have inconsistent ASs. And if you do the research, I mean, I looked at a few of them a few days ago, most of them seem to be multi-homing for this sort of situation. At least I did the traces to these networks and they seem to end up back at almost the same place. So you can find out what they are, show IP BGP inconsistent AS, for example, on iOS. Now, looking at two links to different ISPs, one link's the primary, the other one's the backup. Again, not a very realistic situation, but it's a place where we can actually start from. For 19 aggregate on each link, again, we assume that we've got a /19 address block. We keep announcing it everywhere. Everywhere we connect, we announce our aggregate block. Primary link makes a standard announcement, so we just send our 19 out. We do nothing with it. The backup link, here we lengthen the AS path by using the AS path prepend. We cannot use MED. MED is only useful between you and your upstream ISP. It's between the same AS. If you've got parallel paths to the same AS, MED makes sense. For different ASs, you've got to use the AS path prepend. What the AS path prepend does is you insert your own AS number in your network announcement, and it makes you look further away than you really are towards your upstream ISP. And part of the BGP path selection is shortest AS path. Right, so this makes you look further away. In other words, it makes you the backup path this way. And because we're announcing the /19 out of both links, if the primary link fails, we get backup through the backup link through AS120 in this case. Okay. Again, I've thrown in the router configuration. Router A is nice and easy. We accept the default from the upstream ISP. Notice I'm keeping it simple. We don't need the full routing table. We don't need 100,000 prefixes. We don't need 50. I'm just taking the default. It's all I need. Default is exactly the same as the full routing table. And we're only sending our aggregate out to our upstream ISP as well. And that tells our upstream how to get to us. Router B configuration, well, this is the one that's doing the backup. It's a little bit more complex. It's got the usual thing of sending an aggregate out and accepting the default in. But then we've got the route maps, which are applying the policy. So the outbound policy, we're doing the AS path prepend. And here, down here, you see the prepend. I'm inserting 3 times of AS130. So I'm making it look a really, really, really long way away. When people are doing AS path prepends, only do enough prepends that makes sense. I see some people do 20 prepends. And it's like, well, why are we doing this? What's the point? The internet is only what? 6, 7 ASs deep on average. Maximum depth of the internet a few days ago was 15 ASs, or from my view in Japan. So what's a 20 times prepend going to buy? Nothing, apart from just using up a lot of attribute space. So go to a looking glass and try and have a sensible look and see what sort of prepend you would need. Normally 2 or 3 is all that is required. And for inbound, the default here at the bottom, I've got the route map, which sets local preference to 80. So that makes that path the backup. Default local preference is 100, backup is 80, therefore the other path is the preferred outbound path. So again, it's a reasonably simple configuration. Give it to your customer to go play with, and he'll be delighted. He'll think he's a BGP guru because he can do this sort of thing and he can change it and so forth. Keep the customers happy. Now, this situation is not common. In most sites, if you've got 2 circuits, you want to use them both. But the whole point of trying to show this is to show you the basic concepts. Notice how simple this actually is. We're only relying on defaults. We're making the minimum changes necessary. 2 links to different sites with load sharing. Well, as before, we announced the /19 aggregate on each link. We now split the 19 and announce it as 2 20s, 1 on each link. I mean, yes, I mentioned the net police stuff earlier. Yes, if you take your minimum registry allocation size and subdivide it, it's going to be filtered somewhere. But that shouldn't matter, because you're still announcing the actual aggregate that you've got, or the address block that you've got. And this subdivision of address space will give you the basic inbound load sharing. I mean, okay, it's not going to be perfect. If this works first time, then, well, it's amazing. But for most ISPs, this isn't going to work first time. The point is, it shows you where to start. You start with a big bit, you chop it into two. That doesn't work, well, chop one chunk into two and subdivide, the binary chop. Do it like that, rather than just taking, oh, well, I've got 32 class Cs in there and just spraying out 32 class Cs. Because trying to spray out 32 class Cs leaves you with a nightmare to try and figure out how to make your load sharing work. It makes it really hard. Whereas you do it, the binary chop this way, it's actually much quicker, much more simple. And that's our picture. We want to use both paths. So we send the 19 out both links, 120 out one link, another 20 out the other link. All the traffic for the first 20 will come in through AS100, and all the traffic for the second 20 will come in through AS120. Okay? And that works pretty well. If one of these links fails, well, the 19 that you announce out the other path will ensure that traffic will come in through that other path. And that just works fine. Again, got the router configuration here. I won't go through it. Load sharing is very basic, but it does show the first steps in designing a load sharing solution. Start with a simple concept and build on it. Okay? It's funny, I find this is always the hardest thing, trying to teach people BGP. And I do a lot of BGP tuition around the world, and people always seem to want to make it so complicated. I don't know, maybe it's a part of mysticism that somehow if you break something in BGP, you'll break the whole internet, which is sort of true. If you do something really stupid, you will break things pretty badly. But it doesn't mean that you shouldn't touch at all. So you start with something simple. Hopefully the configuration snippets here in the presentation will encourage you to start with something simple and build it up. Right, more controlled load sharing. Well, I don't know that this is more controlled, but this is another way of trying to do things. Again, we announce a /19. We're always announcing a /19. On the first link, we just announce the 19. We don't do anything else. On the second link, we announce the 19 with a longer AS path, for no particular reason, and we announce the 1/20 sub-prefix. Basically what happens here is all the traffic for the single /20 will come on the second link, and all the other traffic, well, it may come in the first link or it may come in on the second link. Now I'm doing this in preference to taking the 20 and chopping it into 21, or 22, or 23, or 24. And I really hate to see 6 to 8,000 /24s in the internet routing table. But those are there mostly because people are saying, ooh, load sharing, oh yeah, class Cs, chop, 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 chop. Okay, and that's not really a very sensible way of doing it. It's much better, try and do, you've got other tools. ASPath prepend is a useful tool. If you ASPath prepend by single AS, you get a different result if you prepend with 2 ASs or 3 ASs. It depends on your upstream ISP's connectivity to the internet and their upstream's connectivity and interconnectivity. Right? So it's worth checking around with a longer AS path and see what it actually does. This is a lot more sensible than trying to chop address space up into little pieces. So that was the picture. We announced the 19 block on the A to C link to AS100, and the B to D link is where we're doing our fine tuning. Okay, we're announcing a single /20. We're setting a longer AS path, whether it's 1 times or 2 times or 3 times. We may need to announce a /21 out that path, whatever. But we're doing the fine tuning on one particular path. Again, I've put in the router configuration, which I won't go through. This example is more commonplace, and it shows how ISPs and NSites will try and subdivide address space frugally. And frugally is really important. Yes, 120,000 prefixes in the routing table, the routers can handle them these days, the processors are nice and fast and all the rest. That's not an excuse for complacency. I mean, I remember the early days, 94, 93, 94, but just before CIDR was coming out, when we were struggling with whatever it was, 16,000, 12,000 prefixes in the routing table, and that was still just squeezing into, I remember now, was it 8 megabytes of memory and an AGS and so forth? I mean, that was like dire days when we were pushing Cisco to actually put more memory in the routers and put faster processors because the internet couldn't cope. These days, all vendors have delivered big memory, big routers, fast CPUs. So handling 120,000 prefixes is no big deal. It doesn't mean that we get complacent. Okay? Okay, where are we now? Service provider multi-homing. So I'll make a start of this. This is quite a long section. What we've really done up to now is just said, well, default route will do from our upstream ISP. Well, that's fine when the upstream ISP is connecting an end site. Maybe a company network where a company is generally a net user of internet resources. What about the situation where the end site is a provider of internet resources or is indeed an ISP themselves? So I've called this service provider multi-homing, where you're providing things, where you care about which way traffic comes in to the network. So this is a little bit more complex. How do we deal with outbound traffic from a network? I mean, inbound, we know how to deal with. It's how we announce our address block to the network. That's quite easy. But handling outbound traffic is a bit more tricky. You can't just send a little widget out into the internet and say, I want inbound traffic from this network to come this way and other traffic to come that way. Or traffic to go this way, traffic to go that way. You can't do that. Transit ISPs tend to strive to balance traffic flows in both directions. They want to try and balance link utilization, and they want to try and keep traffic flows symmetric. I mean, a symmetric traffic flow is not necessary for the internet. Which again, a lot of new users have a difficulty with. I mean, it's a concept that's a bit strange. But traffic flows do not need to be symmetric. I suppose in the US it's fairly commonplace for this to happen, but US is very much the center of the internet. When you move away from the center of the internet, you really get used to having traffic flows doing weird things, like packets going out of Australia, going straight to the US, and coming back in through Japan and Singapore and through Perth in Western Australia. That's common. You get used to it. But it's certainly not, well, it's not intuitive, and some people are new to it. It's like, why is it doing this? Won't things break? It's like, no, it all works. But still, you want to try and keep flows as symmetric as possible. It doesn't make much sense to have traffic going out, sort of doing the loop of the world just because you can. It slows things down a little bit. Right, so balancing outbound traffic requires inbound routing information. And of course, the standard solution is, hey, here, have the full routing table. 120,000 prefixes? Well, some people would be quite happy with that. But, again, in countries where you can afford to splurge out on a router that can take the full routing table, great. There are many places where you can't do this. And of course, it's absolutely not necessary. I've got Jeff Houston's routing mallet here. You don't need copious amounts of routing information just to solve a local problem. Your load sharing is only between you and your upstream ISP. Why would you care what happens in a network in South Africa or in India? Why do you need that information? It's not going to decide between which upstream ISP you're going to send traffic out to. So why take that information? So, as I say, keep it simple. Keep it simple. It's often easier and a whole load of dollars cheaper than trying to carry n copies of the full routing table. So, some myths, some common myths. You need the full routing table to multi-home. No. People who sell you router memory would like you to believe this. It's only true if you're a transit provider. I mean, if you are a transit provider, you do need the full routing table by and large, because you have multiple exit points in many geographically diverse regions, and it's very hard to try and handle being a transit provider without a full routing table view. And of course, a full routing table can actually be a significant hindrance to multi-homing. When I find that a lot in my travels, ISPs won't multi-home because it's like, oh my gosh, I've got to go and buy XY huge box. I can't afford that. I've only got, I'm not joking, Cisco 2500. They've only got that router. It won't take 20,000 prefixes, never mind 120,000. And it's like they're told by the reseller and their upstream ISP, here, I'll sell you some big thing which they can't afford. And nor do they want to, nor do they need to. Which takes me on to myth 2. You need a big router to multi-home. Why? Router size is related to data rates. Okay, that's where the OC12 and OC48 and OC192s come in. Data rates, that's what the big router's for. It's not for running BGP. You can run BGP on, I don't know, things the size that fit in my hand quite easily. All you need to multi-home is have two interfaces, one for the internal network, one for the external. Be able to talk BGP to at least two peers. Be able to handle BGP attributes. Handle at least one prefix. Actually, that's not true. It should be able to handle two prefixes, UR1 and the default from your upstream ISP. That's all you need to do BGP. And you could probably run this, I don't know, about a few K of memory. I don't know, I'm guessing. But seriously, you don't need a big router to multi-home. Myth 3, BGP is complex. Well, in the wrong hand, yes it can be. I've walked into many networks that are highly complex and I have no idea what's going on. And this is me after 10 years or so of using BGP. Keep it simple. Why do some people love making network configurations highly complex? I really do not know. It doesn't need to be complex. Okay, so those were the myths. So putting those myths aside, what do we do for some real examples? I'm going to look through these 6 examples. I'll probably skip over some in the interest of time, but they're all quite useful. They all require BGP, and they all need a public AS number. The first one, upstream ISP and a local peer. This is a very common situation in many regions of the internet. You connect your upstream ISP to see the net. You connect to the local competition so that local traffic stays local. Well, you connect to the local competition once you get past the thought that your local competition is going to steal all your customers. The local competition only steals the customers if they're better than you. So that's incentive to be better than your competition. Okay, so that once you've got that, it saves valuable dollars on upstream transit costs. Why should you spend a fortune on sending local traffic all the way overseas, or all the way out of the state, or out of the region, or whatever? Yes, this is a very hard sell in many countries I go to, but it should be pretty obvious to most people. It costs lots of money to go this way, and it's very cheap to stay local. You want to try and keep as much traffic as local as possible. That's the simple picture. Your AS110, your local peers in 120, your upstreams in 130. Well, surprise, surprise, you announce your aggregate on each link. To your local peer, you say, this is my address space. To your upstream, you say, this is my address space. From your upstream, you just need the default route. You do not need the full routing table. Why do you need the full routing table? Well, if you want to do data analysis on the internet routing table, sure, it's very useful. But otherwise, it's wasting memory. And also, if there are any changes in the information that comes about the full routing table, say a network somewhere on the other side of the planet breaks, and it sends a withdraw, that withdraw floods and amplifies to the internet, and your upstream ISP gives you lots and lots of withdraw information. You think, wow, a network in, well, where shall I pick on this time? New Zealand is broken. That's really going to make a difference to my operation here, isn't it? I've only got one path to New Zealand anyway. So why do you need the information? So, and for your local peer, you accept all routes. Well, of course you accept all routes from your local peer. Well, all his routes. You don't accept anything he sends, you accept just what he originates. And that's a very simple configuration. You can run this in any noddy router from like the last, 15 years or so. As long as it talks BGP4, you'll be fine. I've put the configuration of router A in, again, for usefulness. This was the connection to the local peer, so you just send your address space out to your local peer, and you accept just his address space in. That's a very simple configuration. You can pick this up and drop it into any Cisco-speaking box, and boom, it works. Alternative configuration, if you're really trusting, is you can do filtering based on AS path. This is if you really know the engineer and the other ISP and you go out having beers with him or something like that, and you know he understands BGP and is not going to make mistakes. Because here we're saying, I trust everything that AS120 is going to give me. Okay? Whereas the previous example said, I'm only going to accept these two prefixes in. Whereas this one, I trust everything he's going to send me. This one means you don't have to change the configuration if he announces another network block to you. Whereas the previous one, if he has another network block, you've got to go and change your filters. Personally, I prefer the previous example, because then accidents don't happen. In fact, what I prefer is what I'm coming to, where I put both a filter list in and a prefix list. Because if I break the prefix list, then my filter list is my backup. As you've seen, if you came to the intro presentation at last NANOG, that's what I said. You saw my template where I've got like the primary configuration, the first backup, and the second backup. You know, I've been around networks long enough to know that people make typing mistakes, and they'll type something in, they check it, and all looks fine, they commit it, and then suddenly, something's broken. Okay? Router C configuration, this is going to the upstream ISP. We accept the default, we send my block out, again, dead easy. This works. This works perfectly well. And you can run this on a very, very simple router. As I said, two configurations possible for A. Filter list assumes the peer knows what they're doing. Prefix list is higher maintenance, but it's safer. Some ISPs do both. If you talk to me and ask me, I say do both, because experience, history. And it's quite simple. Local traffic stays local, and everything else will go to the upstream. And that's BGP. It's a multi-homing BGP configuration. We've got two prefixes from our local peer. We've got one from our upstream. We're handling three prefixes in our IBGP, or in our BGP. Wow. Difficult, complicated. Okay, the next step up is one upstream and a local exchange point. So now there's more than two ISPs in the region. We've got 3 or 4 or maybe 5 ISPs. So rather than having private local peers, we've set up an exchange point. Bill Woodcock has been in and he's done his job, and we've got an exchange point. Very common in many regions of the internet. We connect to the exchange point so that local traffic stays local. Again, we save valuable dollars on transit costs. I mean, upstream ISP is not going to like you for this because you're paying them less money. But that's not the point. You're keeping your local money local. Benefiting the local economy. But I won't get into a rant about exchange points. Right, this is the picture. AS110, router A connects to the exchange point, router C connects to the upstream. Again, you announce your 19 aggregate to every neighboring AS. So router A's got now lots of neighboring ASs rather than just the one. We accept default route from the upstream, either network 0 or any network which can be used as a default. And we accept all the local routes from the exchange point peers. Okay? Sounds easy. So router A is a little bit more complicated now. We've got, again, I've put in far too much configuration, but just so you get the gist of it. The exchange point, fast Ethernet configuration, the BGP configuration, my network address, the network statement there. I've set up a peer group because all the peers on the exchange point have got the same policy, same outbound policy. I'm announcing my address block. So you can put all that in, and then you just set up the peer group to peer with every exchange point neighbor. And it's quite easy. AS100, AS101, 102, 103, and you notice my inbound prefix filters of what I'm expecting from my neighbors. But again, it's a reasonably simple configuration. And then you've got the filters of what you expect to get from your neighbors. Okay? So that's the exchange point router configuration. Again, not complex. It's taking the previous configuration of the single local peer and just scaling it for multiple local peers. And router C configuration, exactly the same as before, so we won't look at that. Prefix list is higher maintenance. Again, if you trust the exchange point peers, you can use the AS path filter if you want to. Some ISPs do both. I would do both. I've got the reverse path forwarding check on the fast Ethernet interface, just in case anybody at the exchange point tries to send me garbage which shouldn't be routed. So that's good to put on as well. And that works beautifully. What about two upstreams, one local peer? Once you've got single upstream and you're doing local peering, you think, yeah, it'd be nice to get another upstream ISP because, hey, there's internet things taking off, and maybe my second upstream ISP will give me a bit of diversity, or maybe it's more reliable or something. So how do you do that? And of course, this is the one where suddenly, because an upstream ISP discovers that you're multi-homing, he says, you need the full routing table. Why? It's only a local difference. So again, full routing table is the sort of standard offered solution. We're connecting to two upstream providers to receive internet, in other words, to get external redundancy and diversity. Exchange point or well, local peer, whatever, so that local traffic stays local. That's our picture. Very easy. So we announce the /19 on each link again. We accept the default route from our upstreams, either the network 0 or the network which can be used as the default. We accept all routes from our local peer. Nothing new. Again, we're keeping it nice and simple. Router A. Well, router A's configuration is unchanged from the single upstream, single local peer example. Router C, that one is unchanged from the previous example as well. We're going to accept the default route from our upstream. We're going to extend them just our /19 address block. So that's unchanged. Router D, well, we're not going to change anything here either. We're just going to accept the default route from router D and send our /19 to router D. So that's the basic starting configuration. That works really nicely. Because the first question that you would ask is, well, how do I control outbound traffic? If you're getting two default routes, what do you do with outbound traffic? Because all that's going to happen here is we're just going to take nearest exit. And that may not be suitable. You want to have some traffic engineering capability so that you can decide between which upstream ISPs you're going to send your traffic to. Okay? So, as I was saying at the bottom there, load sharing needs to be better. It's not particularly useful for international links, to be honest. The better configuration options, well, the two. You can accept the full routing table from both upstreams if you want to. It's expensive and unnecessary. You don't need 240,000 paths on your router. Well, you can if you want. You know, if you like spending your money on expensive equipment, off you go and do it. Accept the default from one upstream and some routes from another upstream. Amazingly enough, that is the way to do it. If you accept the default from one upstream and some routes from the other upstream, then you'll actually get a really good mix of load sharing. Okay, first we'll look at the full routing table version. Well, we've got a /19 in there. The important point is inbound filter blocks RFC 1918 and other non-routable address space. So again, Rob Thomas again publishes that list of what should go on that prefix list. He does it for Cisco iOS and Juniper Junos. So you can pretty much pick up that list and drop it into your router. You must use that for any eBGP inbound, especially where you're getting the full routing table. Outbound, you just send your address block, and then you've got some policy, route map, AS130 load share. AS130 load share, what am I doing here? Well, I'm doing some things. Well, AS130 is my upstream ISP, and what this is actually doing is it says for any prefixes that come from AS130 and AS130's immediate neighboring AS, we're going to set local preference 120. And everything else we're going to set local preference 80. So in other words, any traffic that goes out from my network and has a destination in AS130 or AS130's neighbor is going to go out through the AS130 path. Okay? That makes sense. You want to try and keep the path as short as possible. You want to keep the routing or the traffic flow symmetric. Because any traffic that's going to come from AS130 to you is going to come over that link. It's not going to go around the other way. And it's more than likely for the immediate neighbors as well. It's going to come in from the neighbor to 130 in over 130's link. So this way, I'm trying to get reasonably symmetric traffic flow in the network. This is full routing table. Router D, well, router D I just leave. Okay, just get the full routing table with my prefix list there, throwing away private address space. So that's one way of doing it. And I see this quite a lot. And it's like, well, it's an expensive way of trying to do things. Because you're taking two copies of the routing table and just using local preference to try and do your traffic engineering. Okay? It's like trying to carry two large sacks of things and sort of trying to maneuver them onto a trolley or something like that. Two full big bags of stuff is very, very hard to try and move around. Okay? You want to try and make life a little bit easier for yourself. So that's a description. It's expensive. We need lots of memory, CPU. You need to play the preference games, which can be very hard to do. And you do need a lot of fine-tuning for this. It's much better to actually take partial routes. Okay, if you take a partial routing table, it makes it a lot easier. So on router C, what are we going to do here? Well, we've got an inbound prefix list, which is going to send us, well, it's going to throw away all the private address space and other non-routable prefixes as before. The no-def, well, I haven't put the prefix list in there, but it's basically one that's going to allow the default route to be sent, because our upstream ISP is going to send us a default route as well. We've got a filter list 10 inbound, and a route map which is going to tag the default route with a low local preference. Okay, so we look at this. So again, we've got the same inbound filter list. We want traffic that goes to AS130 and 130 neighbors to go out the 130 link all the time. And this is the way we do it. We match on any prefixes that originated by 130 or 130's immediate neighbors. And what do we do? Yeah, we match on those, and those are the prefixes we actually allow in. Okay. Now AS130 is also sending us a default route. So he's basically sending us, we haven't told AS130 to do anything. We've told them, just send us the full routing table. Because they can either do full routing table or default route. But because you're trying to do some traffic engineering, load sharing, you get them to send the full table, and then you filter out what's on the table. Right? So this filter list here, filter list 10, is basically accepting only the prefixes from AS130 and AS130's neighbors. Right? The prefix list here is throwing away all private address space, but it's accepting a default route as well as the full routing table. Yeah.
So does this example assume that 120 isn't directly pairing with 130 and that 130, AS130 isn't renouncing AS120's routes? Because it seems like if that were the case, you would send all of AS120's traffic to AS130, but everything that wasn't directly AS130 connected to AS120.
You'll see in the AS120 pictures got a similar concept. This one's hearing all the routes from AS130 and the default. So it assumes that 130 is not directly connected to 120, but then again, if 130 was directly connected to 120, you'd hear the routes this way as well, but because 120 is directly connected to 110, that would be the best path anyway. Okay? But it would still be the backup. If the link to 120 broke, you have a default route there that's your backup, and you have the specific paths through the filter list as well, which is a backup. So you've got double backup. Okay? So you see what's happening. AS130 is sending us the full routing table. We don't want it. We're just accepting the default route plus prefixes originated by 130 and prefixes originated by 130's neighbors. And that's what these two lines are doing. And the policy that we've got here is basically saying the default route, we're going to set a local preference 80. The default route that we hear on the other peering with router D, with AS120, the default route with local preference 100. So that will be the preferred path for everything. Making the default 80 on this box makes it the backup. Okay? And that, again, is an example of how you try and do some load sharing. So router D configuration is just standard. We get the default route from our upstream, and that's all we need, one prefix from them. So this example might be something like 500 prefixes from AS130, one prefix from it was 140, and that is pretty much it. Okay? So a description of all that. Router C configuration, we accept the full routes from 130, or we get them to send less. We filter the ASN, so only 130 and 130's neighboring ASs are accepted. So that substantially reduces the routing table. We allow the default, and we set it to local preference 80, so that gives us backup. Router D, remember, here's the default from AS140, and that is the default. So all traffic will go out through router D, apart from traffic that goes to 130 and 130's neighbor. Okay? So partial routes, it's not expensive. You only carry the routes necessary for load sharing. You need to filter on AS paths. See, with this case, you need a little bit more knowledge. But was this configuration more complicated than the full routing table configuration? When you're using the same filtering, you've got the same AS path filtering and so forth. So, quite frankly, it's easier doing this. You've got the same difficulty of configuration, or relative difficulty of configuration. You're just not carrying 240,000 paths on the router. Okay? And just to finish this off, when upstreams cannot or will not announce the default route because they've got some operational policy against using default originate in BGP, just use an IGP to propagate the default from the edge or peering router. Some ISPs won't do a default originate, which just can be a bit annoying. But that's not a problem. Just use your IGP to originate the default into the network. And I've just put in a quick example of how you might do it on iOS. It doesn't really matter. Right, service provider multi-homing. So I've made it a little bit more complicated now, so I'm going for 2 tier 1 upstreams, 2 regional upstreams, and local peers of various descriptions. I suppose this is about as complicated as it could get for, I suppose, a reasonable, a sizable ISP. I mean, they've got the 2 upstreams and they've been to their exchange point. Now they've added some regional peers as well to get some regional routes that they don't want to send all the way through their upstream ISPs. I'm not going to even try and address how peering works between tier 1 and tier 2, mostly because I don't know anymore. And there's no point in me telling you how it worked 5 or 6 years ago, because that's probably not current. So this is a complex example. It brings together all the concepts we've learned so far. We're connecting to both upstream transit providers to see the internet, which is fair enough. And that gives us external redundancy and diversity. It's really the reason we want to multi-home. We're connecting to regional upstreams to give us a less expensive and lower latency view. The idea being is if you connect to ISPs who are in the same region as you, you then don't have to send the traffic through your upstreams, and it might be cheaper. Of course, if it's not cheaper, it doesn't make any sense to do this. But I'm assuming that the further away you have to go, or the bigger that you connect to, the more expensive it's going to be. So if you're connecting to a regional upstream, then it's less expensive, lower latency. Lower latency should mean that customers are happier with their internet performance from you. And you connect to private peers for local peering purposes. You connect to the internet exchange point locally so that local traffic will stay local. And again, all about saving money. So that was what the picture would look like. I've separated each router. I don't think you'd really need to separate each router if you're doing this in real life. But I've separated so the configuration snippets I've included are all distinct. What you would probably do, depending on the size of your network, is have 2 external routers. So one external router will have your upstream ISP, one regional upstream, and maybe one link to the exchange point, and the other one will have the other upstream, the other regional, and the other link to the exchange point, for example. So what we're going to do, we're going to announce our /19 aggregate, our aggregate block on each link, as we have always done and always will do. It's really important to keep announcing your network blocks. You want to accept partial or default routes from the upstreams. I mean, this one, you could accept full routing table from all of these. Would you really want, 4 copies of the full routing table? Well, if you want to carry, 500,000 pounds, fine. I mean, a lot of routers can do that, but that's not the point. especially when you get an update being sent across the net and you're going to hear it 4 different times, and hopefully only once from each of the 4 links and not 10 times from each of the 4 links. And then you've got a lot of CPU for stuff that has absolutely no relevance to you whatsoever. So we're going to use accept partial or default routes from upstreams. So that's either network 0 or a network that we can use as a default. From a local peer, we're going to accept all routes that they originate. From the regional, it only makes sense to accept the prefixes that are local for them. So them, their customers, and anything else that may be useful. So again, that's a discussion you have with your regional. If they want to offer you transit to the internet, as I'm going to show you in this example, that's fair enough as well. But imagine that the transit that they're going to offer would be not as good as your direct links. But again, it's not a bad idea having a backup. When your 2 upstreams go belly up for whatever reason, at least you get transit to somewhere from your regionals, and that's a useful thing to have. I mean, yes, it's more complex, but it is very typical, and you don't need to make this really, really convoluted either. So, router A, that was our connection to the local private peer. We're going to accept all local routes, local traffic stays local, we use a prefix and our AS path filters as I've shown you before, and we use a local preference if it's needed. I'd imagine that the local preference is not needed unless the local peer is at the exchange point as well. And then you may want to have the decision of, do you want your local peer, private peering traffic to go across the exchange point, or do you want it to go across your private link? I would imagine that if you're paying money for the private link, you'd probably prefer the traffic to go over the private link rather than the exchange point. But, whichever is more reliable. Router F, that's the local exchange point peering. You want to accept all the local routes from the exchange point participants. Transit across exchange point is a really bad idea. Yes, some people will do it. You can do transit at an exchange point location, but actually running your transit traffic across exchange point fabric is probably not a wonderful idea. Why not? If you're running transit across exchange point, it means you're carrying a full routing table or default route on the exchange point router, which means that anybody at the exchange point, whether you peer with them or not, can point a static default at you, and voila, you're providing transit for them whether you peer with them or not. So exchange point router should only carry the routing table that is local to the exchange point. Anything else means you can be ripped off from transit. Philip experienced twice. We were ripped off twice in the UK through that manner. People simply pointing static default routes at us. And they did it at May East as well. And this particular ISP actually got free transit. I mean, they only had 2 routers in the entire network. One of them was in London, the other one was in Washington. And, well, anyway. Enough of the details. So, don't carry full routing table at the exchange point. Don't ever do transit across the exchange point. Just there for local routes. Okay, router B is connecting to one of the regional upstreams. They're going to provide us transit to the internet. They are going to have a longer AS path than the tier 1s we connect directly to. So that's fine, that we can use them as a backup. So we're going to accept all regional routes from them. So for example, I've said we're going to accept everything from 150, which is their AS, and anything from a neighboring AS. So the numbers in square brackets basically is a pattern match on any number between, well, any number pretty much. So any AS. We ask them to send a default or send a network which we could use as a default, and we make this one, make local pref on this default 60. So it's really low local preference compared with others which are going to local pref at higher values. And these will provide a backup to the internet only when the direct tier 1 links go down. So that's fair enough. That's that configuration. It's reasonably easy to draw up. Router E, which is the other regional upstream, on AS 160, so we do the same thing, for example, 160 and then immediately neighboring ASs. We ask them to send a default or a network we can use as a default. We preference their default to 70. So they're slightly more preferred than the previous one. And again, they'll provide a backup to the internet when direct links go down. Router C is the first tier 1. We accept all the customer and AS neighbor routes from them. So again, it might be 130 and neighboring ASs. we might choose to accept more from them. It all depends on the actual topology. I can't give you an exact do this, do that, because it completely depends on the topology that all these ISPs have around them. But I mean, again, if you want to search or research the topology, go to a looking glass. There are many, many looking glasses around the internet, and you can just go and figure out how your potential upstream ISPs are connected to the rest of the network. The default that they send, we make local preference on that 80, so they become pretty much the backup for the second tier 1 that we see next. And the second tier 1, we ask them to send a default. Our network we can use as a default, and we have local preference 100 by default. And that is all we need to do. I mean, look at the size of the routing table we're going to get out of this. With the choice full routing table, 500,000 paths, or we had one prefix from D, we probably had 1,000 or so from this one, 500 or so from that one, 500 or so from that one. Say 2,000 prefixes, 2,000 paths, much nicer than 500,000. And you can run this in small routers as well. They don't need to be big. And the summary of all that, local traffic goes to the exchange point, the local peer, the regional traffic goes to the regional upstreams, everything else is shared between the two tier 1s. You get enough detail from the first tier 1 so that traffic between you and them and their customers and their neighbors goes to them, and then everything else you send to the second tier 1. And by fine-tuning what you accept from the first tier 1, you can get pretty good load sharing. The case study, which I'll show you at the end of the presentation, follows exactly this recipe that I've got here. And these were guys who were told, who basically were refused a connection by one of their upstreams until they bought, quotes, a Cisco 7200 router to carry the full routing table. And these guys, the entire network spend didn't even amount to buying one of those boxes. It's a few years ago.
If you have local peering, let's say an exchange like PAX or somewhere else, wouldn't you want to prefer a local peer over a trans provider? In fact, they're going to be giving you direct connection to a network rather than going to a trans provider, which is going to, well, hopefully that'll cost you money, or a peer doesn't cost you anything.
Yeah, sure. Yeah. I mean, you're going to choose the path that really costs you less, and that's probably easiest for you. So, I mean, certainly if you go to the likes of PAX and connect to somebody there, you're going to choose that rather than any transit provider. Sure. It all depends on topology. I'm sort of trying to keep it generic enough so that people can think and apply this to their local situation. Because I'm kind of afraid of coming up with recipes, because some countries, some people will just take recipes and apply it and then start blaming me for things going wrong, which has happened before. It's like, you said this in this presentation, we tried it and it didn't work. And it's like, well, yeah, but... So it's to try and think about the dollar cost for each of the connections and what makes most sense to do. Some people are quite happy, for example, going into a location like the PAX, signing 1 or 2 private transit agreements and relying on the exchange point for everything else that they do, and that works perfectly well. And others manage quite happily without going any new exchange points at all. So it just all depends. Yeah, so that's pretty much that one. Okay, what about outbound announcement strategy? What do we send out? And that determines incoming traffic flows. Well, we're again assuming we get our /19 aggregate. That's our address space that we have, and we send that to everyone. We assume that we send that to everyone all the time. Okay? Keep announcing it, because if any link disappears, announcing this aggregate somewhere else will ensure that traffic will find its way back to you. You can use /20s or 21 more specifics if you want to improve or modify the load sharing. You can also use ASPath, prepends, and all the rest that we discussed earlier. The important thing is not to just say, oh, need to load share, let's chop this up into small pieces. Okay? Try and do the binary subdivision that I was mentioning before. You've got a 19, chop it into 2, see how you go. Look at how your address space is actually numbered across your backbone. Have you numbered your dial pool all there and they're generating the most traffic and the rest is sparsely used for infrastructure? Well, maybe put half your dial pool down here, another half up there, and then load share based on things like that. There's also all kind of tricks that people did with numbering within their own backbone. You can renumber dial pools really easily. Renumbering customers is hard, but renumbering dial pools is quite simple, so you can play around with that to try and aid load sharing. What about unequal circuit capacity? ASPath filters are quite useful there, just depending. You can accept less prefixes if you've got a smaller circuit, or if it's a bigger circuit, accept more prefixes and so forth. You can manipulate that all quite effectively. And if the upstream will only give you the full routing table or nothing at all, again, you can give you the full routing table, you can throw most of it away. I mean, full routing table, you can still download a full routing table on a 56K circuit, 64K circuit. It's going to take a while, but once you've got it all in concept, then you're only dealing with updates. And updates you can pretty much handle quite easily. It's low overhead. Okay, so that was the big one. I didn't put any examples in for the configuration examples in for that one, but I'm sure you can build together the previous configuration slides to work out what you have to do. This one I put in for amusement. It doesn't really happen in North America, not that I'm aware of anyway, but it has happened in Australia where I live, and it has happened many times in India where I've worked. So, and it's actually quite a real problem. ISP runs a large network. The network has no backbone. They've only got points of presence in what turns out to be major cities. Because the backbone between the major cities, the biggest circuit they can get is like 128K or 256K or something ridiculous, whereas within the city they're running like an OC3 or OC12 backbone. So it's pretty hard to join them together on 128K circuits. And basically what happens is each POP will have to multi-home to its upstreams. This is common. And I've just put this in to show how it was done. This all came out with an argument that one of the people I was working with had with APNIC. Because APNIC actually do have people who understand how BGP works very well. And they were saying, but you can do this. And the customer was looking up his reference manuals from about 10 years ago saying, no, but this doesn't work. It's all illegal. So, of course, I was asked to try and mediate. And then said, well, this is how you could do it. It's really a decision whether you want to do this or not, this way. And so that's a picture. They're connecting to exchange point as well as having their own network. They've got two upstream ISPs, AS110 and 120. It works fine with one AS number. Sure, it works with 4 AS numbers, but it works fine with one AS number. Again, because you've got no BGP loop detection problem. Each city operates as a separate network, and it uses defaults and selected leaked prefixes for load sharing. And of course it peers at the local exchange point as well. And, well, router A was the one that connects to, where does router A connect to? Okay, it was in City 4, it connected to both AS120 and AS110. Okay, I know it's not my perfect situation where you've got separate routers, but I'm trying to do it for just sake of keeping the configuration easy. And so I'm accepting the default route from AS120, just sending my /19 out to them. For AS110, I'm accepting the full routing table, but then I'm filtering prefixes. So they're sending me the full routing table plus the default route. I'm throwing away most of the full routing table, only taking their originated prefixes and the prefixes originated by their neighbors, and that pretty much works. Of course, I've got all the exchange point peers as well. And this is what I'm doing, the same as before, accepting neighboring AS prefixes and the neighboring AS plus their neighbor prefixes. And I just fiddle around with that. I can add another match in there if I want to if I need more load sharing control. And that actually works really well. I part my static default towards one ISP, rely on the default route from another ISP, and if any link breaks, then I get back up through that alternative path. Now, why does this work with one AS? Because I don't need to hear the routes from my other satellite or island ASs, because I'm relying on default routes. I'm always relying on the default to get to them. Okay? So if I want to get to City 3, I just rely on my defaults to do that. Again, either go out through AS110 default or through the AS120 default. And it just works. It works fine. Now, the reason we do this with one AS, when the time comes that inter-city bandwidth actually becomes available or cheaper, then we can actually join these cities together and we don't have to go and rebuild a BGP. We just need to set up an iBGP session between router A and B and C and D and so forth. We don't need to change any AS numbers, and it's virtually no disruption whatsoever. And that was the win for me as I saw it, thinking as a network operator. Because I didn't have any problem doing it like this. I got all the traffic engineering I wanted. I could reach my neighboring POPs easily enough. Conceptually, it looks a bit weird because it looks as though it could be sort of illegal. But in fact, it all works pretty well. And when I scale my network to join my cities together, then it all just works fine as well. So just a summary, peer with AS120, I received just the default route. I announced my /22 address. Oh, it was 22 in this case, okay. I peer with AS110, receive a full routing table, I filter with the AS path filter, announce my /22, point the backup static default, distance 252 in case the link to AS120 goes down. Okay, that works fine. Notice one gotcha here. We had a /19 address block for the ISP, but he can only announce /22s from each site. He can't announce a /19. If he announces a /19 from one city, and one of the other city links lost both their connections, where would the traffic go? It would go to the one that was announcing the 19. And that may not be a good idea. Or it may be, I don't know, it may not be a good idea. I wouldn't particularly do it. So this is one of the instances where the net police filters get in the way. Because we've got /22, which people who filter on the registry boundaries are basically going to throw away. And there's no /19 announced. Now, you could work around it by announcing the /19 anyway and hope that your /22 announcements get far enough that they override the /19 that's out there. And by announcing the 19, that you'll actually be able to get to some of the people who do filter. But that's starting to get a little bit hacky. But it's one of the workarounds. Okay, default ensures that the disconnected parts of AS100 are reachable. The static route will back up the 120 default. There's no BGP loop detection because we're relying on the default route. Okay, and as I was saying, announcing the /19 aggregate could lead to problems. You know, if one city disappears, then you suddenly get traffic that's basically got nowhere to go landing in the city that announces the aggregate. But if you cope with that properly, then that may not be a problem either. Okay, this one is harder to do. I put this in response to a question a few nanogs ago from somebody from an IDC, Internet Data Center, who said, well, we're not a registry member, so we don't get our own address block. What do we do? And, well, the answer, I'm afraid, is it's pretty hard. If you're not a registry member, life does get a bit harder because your address space comes from elsewhere. The situation is also true for small ISPs and for many enterprise networks. Where smaller address blocks are being announced, you can't really go about subdividing address space. You're going to have to announce address space you receive from one ISP out the link to another ISP. Some ISPs don't let you do this, and it just gets a whole lot more messy. And of course, for a data center, outbound traffic paths do matter. They don't care too much about how traffic comes in, but they do care how it gets out, because they're supplying data content to the net. One thing I think would be very useful for address space is to try and get address space from both the upstreams and try and portion the address space according to the size of the circuit. Now, most IDCs are connecting with whopping big bandwidth, like 100 megabits and so forth. So that's generally not too much of a problem, but again, there are many places where they don't have that facility or that luxury. And the circuit sizes could be varying. They're trying to portion the address space according to the size of the circuits makes more sense. So it could be something like this. We've got two local peers. Well, local peers we don't care about because by local means they're in the vicinity, so we can run big fat pipes to them, no problem. It's going to the upstreams in AS130 and AS140 that could be more the issue. So let's say we're assigned a /24 from AS130 and a /23 for 140. The circuit to 130 is 2 meg, the circuit to 140 is 4 meg. Okay, so we've got address space according to the circuit sizes. I'm kind of assuming that every host or server in the data center is providing the same sort of outbound data volume, which again may not be true, but I've got to start somewhere making my assumptions. So the router A and B configuration, inbound we should accept all routes from AS120 and AS150. So 120, remember, and 150 are the local peers. So they're all the local routes. We want to try and send all the local traffic local. Outbound, we should announce all our address space that we have, so the 24 and the 23s. I mean, announcing 24s and 23s to local peers shouldn't be a problem. If we have a local peer who's filtering on the registry minimum allocation size, then we should try and find other local peers. It doesn't make much sense to do this for private peering. Router C configuration, we accept partial routes from 130, so as we've done before, anything originated by 130 and anything from the neighbors. Inbound, we ask them to send a route we can use as a default, and we set local preference to 80 on that, so it becomes the backup. Outbound, we send our /24, which is what we got from them, and we send the 23 with an AS path prepend of 1. Okay? So we're assuming that the other AS will allow us to send out that /23, which I say some ISPs don't let you do this. But assuming we can, then we send a 23 with a single path prepend. So traffic for the 24 will come in through 130. Traffic for the 23 hopefully will all come in through the other path, through router D. And router D, we ask for a route we can use as a default, and we leave the local preference at 100, so it's a higher local preference than we get from AS130. Outbound, we send the /23, and we send the 24 with a single prepend. So again, the traffic for the 23 is attracted in through that AS, and the backup for the 24 comes in this way. Okay, so that does our outbound traffic load balancing, which I said inbound traffic load balancing, which, as I said, we don't particularly care too much about, but we do care the other direction. Okay, for local fine-tuning, I'd say just increase circuit capacity. I don't think for local peer circuit capacity is much of an issue. I mean, any metro area that I'm aware of, anywhere around the world, it's generally pretty easy to get local circuit capacity. However, for long distance, that's a lot harder. For inbound, well, you can modify the AS path filter on router C. So that gives you a bit more variety of outbound traffic. For outbound announcements, well, we can modify the AS path prepend on router C and D to determine how traffic flows in. But that's pretty much all we can do. The inbound policies do need to be carefully thought out, okay? Because the outbound traffic flow is really what matters to us. So in other words, what you receive from your neighbors. Okay, so you have to do a lot of playing around with this. I don't think there's much value in trying to take the 24 and chopping it up into other pieces, certainly not for that direction. And I don't know if there's much you can do with your upstream ISP either to try and do it. The AS path filter, the prefixes you learn from your upstream ISP are pretty much all that you have available to play with. Redundancy, well, circuits terminated in separate routers. You need to try and apply some thought to the address space used. Say request it from both upstreams. It's generally quite useful to do that. Of course, your upstreams are going to announce just their blocks to the internet. They're not going to announce you as specific /23s. So the internet's only going to see the address blocks. They're not going to see the specific prefixes. So that could have its own interesting side effects as well. Okay. And then try and use address space evenly across the IDC. So for every customer who connects, who gets an address block out of the /24, you want to give 2 to the /23. So you keep it reasonably even, and hopefully you've got even amount of outbound traffic out to your network. As I say, it is pretty hard trying to do the load sharing in this case. But I mean, these are some of the techniques that you can actually think of using. What about failover? Well, because you're announcing the 24 and the 23s from that upstream blocks out the other upstream. As I say, if they're filtering what they send out to the internet, you could end up with problems. If the two upstreams are connected to each other, then it's not an issue. But if they're not connected together, then you could well have a problem. Because if your 24 disappears and is part of your upstream's block, well, sure, your upstream's announcing his whole address block to the internet. Traffic which is meant for your 24 comes to him, but your link is down, there's nowhere else it can go. So that is a problem. So you have to work with your two upstreams to get them to agree to exchange routes, or maybe agree to leak your prefixes to the internet. Okay, the final chunk of this presentation is all about using communities. Now, most of what I've talked about has been simply using local preference and MEDs and ASPath and all the rest. But communities are actually really important when it comes to multi-homing. In fact, any type of eBGP connection to the internet. So I'm just going to have a fairly brief look at how you can use communities for a lot of eBGP sessions, multi-homing type configurations, and so forth. All right, so how they're used in practice. Well, the first one I want to draw your attention to is RFC 1998. That is quite an old RFC, but it's informational about how Internet MCI used communities for customers who multi-homed onto their network. It describes how to implement load sharing and backup on multiple inter-AS links. So specific communities were set aside within their network to implement multi-homing. And the good thing about this, it gave control to the customer, as I was talking about before, and it simplified their configuration greatly. I mean, when this RFC was published, we adopted it in our network in Europe, and we used this for all our own connections. We gave it to the customers could go and play around with all sorts of communities, and they were really happy because they were playing with what was then a really new BGP toy. Communities only had just appeared within iOS, and I was like, wow, they had the latest image and they're playing with all the latest things, and they got really excited by it. And we were just happy because we didn't have to go fiddling around with our configurations so much. These were the particular values. Your AS number :100 meant we set local preference to 100. AS number :90, we set local preference to 90. If we had that particular community on the prefix. If we had community AS number :80, we set local preference to 80 and 70 and so forth. So :90 is if the backup route, it's the backup route if we're dual homed on this AS. :80 is if the main link is to another ISP with the same AS path length, and 70 if the main link is to another ISP. Okay? So those communities meant particular things, and if we had it, our AS number that community on a prefix from our neighbor, we would set local preference like that. Of course, if somebody sent us those communities by accident, we would local pref them anyway because we didn't know any better. Those were what we used. We published them officially in our AS object in RIPE's database. So, sample customer router configuration. We would put something like this on our customer router. It would just print out a template. The route map there would do all the community configuration. We'd send a community like that. The access list there, the ASPath filter, basically if anything is originated in the local network, which is what the $@ means, we would then set community 100:90, which tells AS100, I want this to be the backup path, set local preference 90 when you hear any prefix I send. And that was a simple configuration that we set. And you see what customers can do. If they've got this configuration, you tell them, change that 100:90 down there, how you wish. You can set it 100:100, 190, 180, 170, according to these conditions, and your multi-homing configuration would automatically change on our network. And they're like, wow, can we do this? And of course, they would then go and try it out and see how it all worked and so forth. That's just a one-line change that the customer has to make. They go in there and change the community value that was set. Now, how it made it easy for the ISP? Well, on the aggregation router, all you need to do was put this sort of configuration on. You would have different community lists, which basically allow you to match communities. So if you had community 100:70, we would set local preference 70. If we had 180, we would set local preference 80, 190, set local preference 90, and so forth. And that was used in a route map, pretty much like this. So route map, set customer local preference. So step 20 was we match community 180. If the prefix has that community set, we would set local preference 80 on the community, and so on through all the other possibilities. And that was there. It was always part of our BGP configuration. And all the customers just had an inbound route map that said set customer local pref. And any prefixes they sent with communities that matched these, had the local preference automatically set. Of course, some of our bigger customers in Europe would have lots and lots of different address space. So they may have some /24s, they want one local preference set. They may have a 22, they want another local preference set. So they could chop and change. And it's amazing some of the stuff that they did with the multiple connections to us and to other ISPs. We've got some really weird and wonderful load sharing configurations. And the beauty of it all was we had to do nothing. You just sat there and thought, yeah, off they go and do it. And there was, some of the banks and some of the broadcast people did all this, and it just worked wonderfully. Of course, as time went on, we found that we had to add other things to it. They want to do other things, and I'll discuss that in a little bit more time. As for supporting RFC 1998, well, what I mean really here is I'd like to see more ISPs actually use communities within their own networks. Very few of them seem to do that. They just seem to think that communities are too hard. But start with this RFC. I mean, it's really simple. The configurations are all out there. Put it on, at least you can offer it to customers and give them the fairly basic thing they can go and play with. Understand how it works, then you can make it a little bit more complicated, and so forth. Some of the ISPs will put it in the AS object in the Internet Routing Registry. Now, I've never seen anything in the RADB or ARIN's routing registry about this, but if you look in the RIPE routing registry, you'll see lots and lots and lots of ISPs who will document the community policy. And that's what I'm going to come on to a little bit later on. So how do you use communities for two links to the same ISP, where one link is the primary, another one is the backup? This is just showing you how it could be done using communities. So this is just stolen from way back at the start of the presentation. We're announcing a /19 aggregator in each link. Primary makes standard announcement. Backup link, rather than sending an MED, we're going to send a community. When one link fails, the announcement of the aggregate, blah, 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 blah. Okay? So we're doing the standard stuff. So router A configuration, well, this is the primary path. It's the same as it always was before. We just basically send our aggregate out. We accept the default in. Router B, rather than using communities, rather than using MEDs, we're going to use communities. So I've added in a send community line because we're going to send communities to our neighbor. Otherwise, we're going to send our aggregate out, accept the default in. The route map, router D out, rather than setting an MED, is going to set a community, and router D in is going to set a low local preference as it did before. Okay, so router D in, we're setting a low local preference here. Router D out is slightly different. Set community 100:90. Remember, community AS number :90 told your neighboring AS to set local preference 90. Other words, make this path the backup. And that's it. Now, if you look at it and you think, well, why should I use communities for this? Hey, it worked fine with MED because I just put an MED in there. That's true, but this is a very simple case. But if you're looking to scale this, well, if you as the ISP are looking to make this scale for your network, offer other weird and wonderful things for your customers to be able to do, then this is a much better way of doing it. I mean, yes, this looks probably more complicated than MED, but this scales a lot better. Router C configuration, it's the same as before. Router D configuration, well, it's a little bit more complex. Route map, BGP customer in. Okay, we now need an inbound policy. Before, we just had an MED coming from our neighbor, and that was it. We didn't need any of this stuff. Now we need some inbound policy. And that route map, well, I've snipped out the unimportant bits, but basically, BGP cust in, match community 90. In other words, if we match 100:90, we set local preference to 90. Okay, so I've snipped the bits out just to make it fit on the slide. Okay, so that's typical of what you put on the ISP aggregation router. And of course, if you're aggregating lots and lots of customers, this makes it nice and easy. You always apply this route map inbound for all the BGP customers. As I say, it's a simple example. It looks more complicated than the same example presented earlier, which used local pref and MEDs. But of course, the advantage, this scales really well. And with larger configurations, more customers, more options, it actually becomes a lot easier to handle.
I've worked for ISPs and talking to them is that the reason more people don't is because communities don't have any intrinsic meaning. And even though RFC 1988 has this one very simple, like, go read what Global Crossing does with communities.
Yeah.
It's cool, but it's just completely different from that.
Yeah.
Do you think there's going to be any collapse or any correlation in the standardization of how people use communities?
And the thing is, RFC 1998 isn't even a standard. It's pure informational RFC about what Internet MCI did. I mean, I suppose it's become a kind of current practice in that a lot of people have adopted those particular values. But as the example you mentioned, people have just picked up any random thing for any, and you've got to know what your neighbor's doing with the community. Communities make no sense more than beyond the neighboring AS. And, I mean, I hear communities from all over the world in my BGP feed that I get for the routing table analysis. And I have no idea what they mean. It's not documented anywhere. I mean, I look in routing registry for the objects there, and some of the ISPs don't even document them. Look in the web pages, look in the attack pages, support pages. There's no documentation. But, some people are quite happy to transit all these communities, and I'm like, I don't know. Is there going to be any standardization? I have no idea. I kind of hope there is, but I suppose it needs somebody to write the document that says, we shall do this. And who's going to do it? I mean, me? Well, you. I mean, the thing is, as soon as you write something saying, thou shalt do this, somebody else is going to stick their hand up and say, well, but we've been running this for 5 years and it's going to be too complicated to change, and if people start doing this, it's going to interfere with our net. I don't know. I mean, even the discussion over some of you may have heard of the no peer attribute. When that, it was trying to leak address space for traffic engineering. If you had an aggregate, you announce, say, sub-prefixes from the aggregate, you could tag them with this no peer attribute. So it would say only go about 3 AS hops through the internet and then be dropped. So it let you do, well, not local traffic engineering, but traffic engineering within 2 or 3 ASs or something. There was some discussion about whether to make that a community. But then it was like, some people don't use communities and other people already use, and so on. So I think we're too late. It's too far. I mean, communities have been around for 7, 8 years now. If it had been done 6 years ago, 7 years ago, it might have been an idea. But I don't know. I've got some examples coming up, so you'll probably get some idea of the mess that, it's not a mess, but it's like the different interpretations that people have. So, anyway, right, here's the working examples. Okay, 1998 is simple it's okay for simple multi-home customers. That's fair enough. It does assume that upstreams are interconnected, which at the time, IMCI's time probably made sense, and they were connected to all the other tier 1s, and it was all nice and easy. The internet was simple then. Now it's anything but, and I'm not sure if the basis of the RFC is actually very useful. As a concept, yes it is, but you need to do a lot more to actually make it useful for you. And ISPs have created many other communities to handle more complex situations, and they've pretty much invented their own thing. Trying to simplify the configuration, that's what they're all trying to do, and give the customer more policy control and more variety. Public policy is usually listed in the IRR. For the examples that I've got here, these are all from the RIPE routing registry. First one, this one's not from the RIPE routing registry. This is connect.com.au, an Australian ISP. They've run their own routing registry in Australia. And if you look in their AS object, these are the communities that they support. Well, they supported the last time I looked. But Mark Pryor doesn't work for Connect anymore, so I have no idea the status. But I'm assuming that they're still there and still supported. And they support those 8 communities. Paid no real attention to RFC 1998 values, but they're using similar concepts. Well, these are the 3 that are the similar concept to the RFC 1998. The first one, 2764:1, announced this to domestic rate ASs only. So those are ASs that connect to Connect that are only paying domestic rate. Australia is funny from the internet point of view because we've got domestic tariff and we've got international tariff, and it's all pay per megabyte rather than what the rest of us are accustomed to. It was very strange for me coming from Europe, going to Australia to discover this cost per megabyte. But Australia is like that, unfortunately, or however. Anyway, so this one will connect to domestic rate ASs only. This one don't announce outside the local POP. And then we've got 3 which are for multi-homing, lower the local preference by 5, 15 or 25. I'm not sure why, but Mark can probably explain it if you ask him. Announce to non-customers with no export. So if you want to connect but not have your network transited by them, you can get them to, well, if you send community 2764:6 at their border router, they will announce it to their non-customers, in other words, their peers, with a no export. So that's quite useful. 2764:7 only announced to customers. So that's bringing it one step closer, and it's in effect the same as, well, almost the same as no export. Not quite, but almost the same. And 2764:8 announced over the satellite connection, which is cheaper. Satellite, well, at those days, I guess, was cheaper than coming over the undersea cable, so you got a different rate. So if you sent them that community, the prefix was sent over the satellite link, which means return traffic came over the satellite link, which meant you got billed at whatever, 10 cents a megabyte rather than 20 cents a megabyte, or whatever the rate was. Okay? That's what Connect used. UUNet in Europe, AS702. Yeah, they've got a few here. 702:80. Recognize that one from RFC 1998. 702.120 went another direction. Okay, so that did a higher than default local preference. We decided we needed that because there's some situations where, well, other ISP we're multi-homed with didn't use communities at all. So they would just send the network with standard local preference, no community whatsoever. So if we could get a customer to send us that, then we would prefer that path. So it's like RFC 1998 in reverse. 702:20 meant announced to UUNet ASs, so the 701 through 705, and UUNet customers. Okay, so that was fine. That meant that the prefix didn't get global reach, it only had within UUNet's backbone. 702:30, keep within Europe. Don't announce to other UUNet ASs. So a customer may have a better transit deal from somebody else, so they'd want UUNet European backbone access, but nothing more. And your customers could change this if they wanted to. I mean, they may decide, oh no, I'm not going to use my transit from cable and wireless, so I'd stop announcing the 702.30 on my prefixes, and suddenly I would get transit from UUNet. So we let customers change these. They still paid us money anyway, but they could do this traffic engineering themselves. 702:1 prepend AS702 once at the edges of UUNet's network to peers. 702.2 prepend twice. 702.3 prepend 3 times. So these were all quite useful to have. Again, it's been a while since I picked these up. I mean, it was last changed in 2001, and I must admit that was the last time I looked. So I don't know if they still do this or it's changed, but that was a good example of what was actually being implemented. Okay, BT Ignite, the former Concert European backbone, now BT Ignite backbone. They've got an amazing list. It would have taken about 3 or 4 slides to actually display the whole thing. But again, in answer to your point from earlier on, yeah, I mean, they've just picked, let's pick some communities and hope that they won't. I mean, they've basically decided these are going to be what we're going to use. Now, I should give a bit of history about these from BT Ignite. These were actually taken from work done at one of the Tiscali networks in Europe. And the guy whose name I've forgotten who was working there, he'd come up with a document and so forth describing all these communities. And quite a few ISPs have actually picked this up. And that's the closest we've got to any type of global thing, I suppose. And I must admit, I did promise to work with them to write this up about 2 years ago. And time being as it is, I've never managed. But quite a few ISPs are actually using this one, which is it's nice to see, because they actually do mean something. 5400 is the AS number, of course. 1000 lists all the European peers, everybody they peer with in Europe. 1100 lists everybody they peer with in the US, and I imagine they might have an Asia Pac or African one as well, I have no idea. So if you send 5400:1000 to the European peers, it means we do not announce this network to our European peers. That's what it means. Community to not announce. So if we send 5400:1000 on our network, on our prefix, we do not announce this prefix to European peers. If we send 5400:1008, it means do not send this prefix to AT&T, and so forth. And I've worked with a customer who's connected to the CIP core backbone or the BT Ignite backbone, and I've played around with these communities. And it's quite amazing the control that you do actually have. And I really do quite like how it's all turned out. Likewise, this column, if you send community 5400:2001, it will do a single ASP prepend of 5400 to Sprint in Europe, and so on. Pardon me, through the backbone. If you send 5400:2100, it will do an ASP prepend to all of the US peers that BT Ignite have. And that's one of the ones that actually used a pretty good effect with that customer. Okay, so these are good examples. Again, I think you can look this up today in the routing registry, and you'll see the full list of what they actually support. So it's quite detailed. And we get yet another ISP who does something completely and absolutely different. This is Carrier One, another European service provider. And here they tag communities on the prefixes that appear at different locations. So if you see community 8918:25, then you know that that prefix has entered the network in Milan. Or 8918:40, you know it's entered in Geneva. And there's a whole long list of other multi-homing things. It's huge. But again, it's completely different from anything else I've seen. So somebody sat down and worked really hard to try and put all this together. And of course, paying no attention to the IRC 1998 effort that Tony Bates wrote up. So another example. And you can use these communities to your benefit if you want to. Level 3, something completely different all over again. So level 3, I think of one global AS, 3356. So they've got customer traffic engineering communities. And the first lot are the suppression ones. So 64960:XXX, announce to ASXXX if 6500:0 set. 6500:0 set, announce to customers but not to peers. So if you can work your way back through that, if you set 6500:0, we announce that prefix to customers but not to peers. And if we send 64960:X as well, then we announce it to ASX also. So we can send this to customers and any peers that we happen to list as well. And peers are listed by specific communities. 6500:X, do not announce at peerings to ASX. So you can follow through that again. You can get a fairly sophisticated type of multi-homing traffic engineering load sharing thing going. The next one's customer traffic engineering pre-pending. In this section, again, paying no attention to the IRC 1998. 65001:0 means we're going to prepend once to all peers. 65002:0 prepend twice. 65003:0 prepend 3 times. If we specify 65001:number, we then prepend once to that peer in that number. Okay? So you can see how it gets reasonably complex. And of course, if you look higher up the AS object, you see who all level 3's peers are. So you can, if you're a customer of theirs, BGP customer, you can have a wonderful time playing around with all these communities, deciding who you peer with, how you peer, and what you send where. It is really very, very powerful. It's probably more powerful than most people will ever need, but it's an example of what you can actually do. Okay, we've got half an hour left. So just to finish off, we want to have a look at a case study. This is a small Middle Eastern, well, it's not Middle East, it's Asian ISP from South Asia that I helped set up the network for a way back and I sort of look after them from time to time. How have they dealt with multi-homing? I mean, they started off, they just had one satellite connection to the internet. But I suppose for reliability, redundancy, and all the rest, the upstream provider probably wasn't being as reliable as they'd expected or wanted. They had to grasp the multi-homing genie and try and do something with it. So they need to multi-home. They need to connect to AS5400, seen them before, and AS2516. Their first connection was to 5400, so there was a static route and it was all nice and easy. The second connection was in Japan. Now with satellite internet connection, where you connect to in the planet is probably not quite what most of you are accustomed to. It's not like you connect in one state and the neighboring state. This is like on the other side of the world. I mean, Japan and UK are about as far apart as you can possibly get. Consider Japan is what, 2 hours away, 3 hours away from the date line, and the UK is pretty much straddling the 0 degrees. So it's about as far apart as you can get. So it made it interesting. They got the /19 allocated by APNIC, they're an APNIC member. They got the AS number from APNIC quite easily. The 1 meg circuit to both upstreams, and that was all working just fine. But they need to multi-home. They want symmetric routing and equal link utilization. Don't they all? I mean, everybody asks for this. Has to be symmetric. Right, you connect to Europe and Japan. Symmetric. Whoa. International circuits are expensive, they told me. You don't say. For them, they were very expensive. But they had 2 Cisco 2600 border routers with 64 meg of memory. And this was like, well, consider they had 4 routers in the entire network. Can't afford to upgrade memory or hardware on the border routers or internal routers. I mean, they basically, if they wanted to carry the full routing table, they needed more than 128 meg. And you don't get 128 meg on 2600s. Therefore, they were faced with buying something bigger. And rather than doing that, I got a little email saying, Philip, can you make this work, please? As though I could magically squeeze the full routing table at that time into 64 meg of RAM, including operating system and everything else that was needed. Of course, I work for Cisco and I could do anything, can't I? Right, so that was what we had. Pretty picture, simple picture. Both providers stated that routers with 128 megabytes were needed. I guess it was installation engineers reading from the standard script. BGP customer, sell them a 7200 or sell them an M5 or something. And it was like, sales opportunity. And I'm like, well, okay, there are no Cisco salespeople in here, or no salespeople at all in here, I hope. So it's those myths. You don't need huge memory just to multi-home. You don't need the full routing table. I hate people just being sold routers just to carry an unnecessary routing table. As I've been talking about most of this afternoon, full routing tables rarely required or desired. Solution, get the default from 1. Okay, KTD were delighted to send a default. It means they didn't have to send a full routing table. They were really happy with us. In fact, they were really happy. I got a very, very nice email from their support person saying, this is really good, it's saving us a lot of resource, and we really appreciate you doing this. And I was like, wow, if I'd get that from anybody else, it'd be amazing. And from the other one, well, it was full routing table or static route, that was it. So okay, that was fine. So we accept partial prefixes from the other. So first cut at the inbound load sharing. I went to a few US looking glasses, because the US is pretty much the center of the internet. I mean, that's just fact of life. It is the center of the internet. So that's where most traffic is going to emanate, originate, or run through. I checked the path to AS5400 and the path to 2516. 2516 was on average 1 hop closer from most of the looking glasses. Therefore, if I set an AS prepend of 1 AS on the 2516 peering, in theory, inbound traffic should be balanced. Fingers crossed. Refinement? Didn't need any. That worked. Okay, I was seeing on average 600 kbits per second inbound on each circuit. But it did vary according to time of day, which I didn't understand. I'm not aware of anybody who's got time of day BGP peering going on within the network, but the traffic load varied. There was more traffic from the the Japanese connection in the morning and more traffic from the European connection in the afternoon. Maybe the customers are reading, US newspapers first thing in the morning and reading European newspapers in the afternoon when they first appear. I don't know. I really don't know. Okay, outbound load sharing. Well, I requested the default from 2516, which they were delighted to send me. I requested full routes from 5400, but their automaton was full routes or static routes. And it's like, well, we want to do BGP. So we took full routes from them. It was easier than trying to argue. I then looked at my routing report. So I picked the top 5 ASNs that were contributing to the internet routing table. I don't know why I did that. It just seemed, let's pick something. And I created a filter list. So the top 5 ASNs then were 701, 7018, 1239, and 7046. So basically, if those 5 ASs were anywhere in the AS path, I would discard the prefixes. I allowed all prefixes originated by 5400 and anything else up to 2 AS hops away. Now I did this in that order because 5400 actually connects to those 5, well, some of those 5 ASs, I don't remember which, but they do connect to them. So I obviously didn't want to allow those in. So I threw away anything that had those 5 ASs in the AS path. I allowed 5400 and 2 immediate neighbors in, and then saw what I got. Well, I got 32,000 prefixes. It was quite a lot. I was seeing a lot more outbound traffic on the 5400 path than I was on the 2516 path. And traffic was asymmetric. It was going out through 5400, going all the way around the world, and coming back in through 2516. 1 second round trip time, what was more than that, was like 1.5, 2 second round trip times were not really very pleasant. Trying to read, for example, the BBC World website, well, getting to BBC World was easy. It would go out through 5400, but all the packets were coming back in through Japan after having traveled across the US and so on. So that wasn't very pretty. So I added the next 3 ASs from the top 20 list. So 209, 2914, and 3549 went in there. Now I got 14,000 prefixes. And traffic was now evenly load balanced going out. There's about 200 kbits per second on both links. And what was even more surprising, it was symmetric. We couldn't find a site. We sat for about a few hours going to most of the sites that the customers were looking at. And we found that traffic was mostly symmetric. It was going out and was coming straight back in the way we expected. And we were actually really surprised by that. So it was good. I think it was more luck than design. But they were happy. They got the symmetric thing that they wanted. They got equal utilization on both links that they wanted. So I went home and they were happy. And that was MRTG graphs I took a couple of weeks later. And it's reasonably well balanced. But you can see the funny time of day variation in there as well. But for example, the Wednesday one has got the low peak, high peak, low peak. Which is, oh well. Just what happens. But that was MRTG graph, and it was pretty symmetric. They were happy with it. I've put all the configuration in here if anybody's interested in the configuration of how it works. I'm not going to talk through it. Well, maybe I will. Got some interesting bits. Oh yeah, that was another one. Can only do eBGP multi-hop for eBGP peerings. We will not do eBGP across a point-to-point link. Well, why not? Because it's bad. Why? No answer. So, well, we had to do eBGP multi-hop. That's all we could do. My guess is they had one router that did eBGP, and it wasn't the aggregation router. Because multi-hop 5 is what we needed. Not even multi-hop 3 worked. It was 5. So that's what we had to do. So that was on router A, went to 5400. Filter list 1. Okay, so the filter list, prefix list in, filter in, and out, filter out. Those in, filter in, basically, yeah, we deny all the private address space. So basically we allowed everything apart from the private addresses and so forth. Basically Rob Thomas's list. Outbound, we just sent our own address block. We had a static default with a very high distance pointing to the serial interface. So the BGP completely died, we still would have an exit path. Okay, next slide. So that was the AS path filter. So we blocked anything with 701, 1, 7018, 1239, 7046, and so on in the AS path. And that threw away the vast majority of the routing table. We allowed 5400, their neighbor, and their neighbors. And that gave us about 14,000 prefixes in total. Okay? And that gave us, we found most of the European backbone. It was pretty good. Most of the European ISPs fitted into that particular thing. Yeah?
So how does this do over time? If you wait a year or two?
Oh, it changes. This needs to be maintained. I mean, what I showed you was about a week afterwards, and it's already changed a little bit. I went back for a second visit, which is the next set that I'm going to come to, and it's completely changed. But, I mean, they would monitor it. They would monitor it over, I think over time I had to remove, I've forgotten who I removed. I think 209 I had to remove from that. And I think 2914 I had to remove as well, because it was starting getting unbalanced towards the Japanese side. So I had to get some more prefixes. And I think just before I visited the second time, I was back to my original 5 again. It's dynamic. See, the trouble is, ISPs are changing who they connect to all the time. And you have to monitor something like this. I mean, yes, you can buy software boxes from different companies that will do this kind of work for you, and that it works out your best multi-homing, load sharing at any particular time. But as I was saying to somebody during the break, I'm very much from the old school. I like getting in there and fiddling around with this, fine-tuning it exactly how I like. And this has to be looked after. When we did this sort of thing, it was the NOC's task, basically every week, to look at what the outbound circuits were doing, especially the circuits across the Atlantic, because we had multiple T3 circuits and so forth. And yeah, they would fill up. And you'd have to move traffic around. We're running eBGP on some, and they would all fill up, and you'd have to move stuff around. So with this one, again, yes, they had to move stuff around. But at least they only had to change one, because the other router was just a default route. And here, we could just add or subtract from this list to try and get what we wanted. Okay. Oh, one thing to note, access the filter list 3 at the bottom there. It permits anything from the local AS. Remember what I said about doing prefix filters and then AS path filters? One backs up the other one. Well, the out filter here sends my aggregate, and the filter list 3 below basically does the same thing. It just allows my aggregate out. But if I blew away my prefix list for whatever reason, then my filter list would be the backup. I've broken too many things in my life, so I always make sure I have a backup. Right, router B configuration, this was going to the other one. Not very much here. They're running a really, really old operating system that didn't even support the route refresh capability, so we had to do the soft reconfiguration hack. So we accepted the default route from them. Outbound we send a /19, of course, and we had the filter list to back it up. Here's the inbound filter list. Notice I'm only accepting the default route, but I put the filter list in anyway. Oh yes, and I'll also put the maximum prefix in too, even though they're only sending us one. So I've got 3 levels of redundancy. It's a complete overkill, but it's there for a reason. So we're allowing the default route in. The filter list, we're allowing prefixes just from 2516, which is fair enough. And outbound, we're just doing the AS path prepend, a single instance of our AS. And that was the config that made it all work. That's the summary. Here's the full table, throws it away. Static default points to serial interface. If link goes down, the OSPF default is removed. We used OSPF for the default within the network for the backup. Router B, here's the default from 2516. If the default disappears, either BGP going down or the link going down, the OSPF default is removed from this router, and so the default from the other one takes over as the default exit point. And this all works beautifully. They get very, very fast failover if the BGP links goes down. So they were really happy with it. And I've given this particular case study in quite a few presentations. I gave it at AFNOG last year, which is about this time last year. And a couple of the ISPs took this away and implemented it on their own networks. And they're like, wow, it just works. It's great. I don't have to go and buy huge routers. And they have little boxes, 2500s, 2600s, and so forth. They're really, really pleased with it. And it's serving their need. So as I say here, multi-homing is not hard, really. Just needs a bit of thought, a bit of planning, If you're going to start off, try and use this case study as an example strategy. We've tried to keep it simple. We're building up. We add more prefixes to make it more complex. Okay, here's my second visit. This was last year. Was it last year? I think it was last year. Okay, we know all that stuff. We want to add a new satellite connection, 640K link to Germany. And of course, they still want symmetric routing, equal link utilization. Usual thing they told me, it's all really expensive, we've spent lots of money on this, and but they've run into some money, and now they've got bigger routers, and they've got full of memory, and they want to carry the full routing table. And I'm like, why? What was wrong with what you've got? Well, nothing, but isn't the full routing table better? You've just contradicted yourself. You've said nothing wrong with what you've got, but full routing table's better. Explain to me how it's better. But everybody else does that. If everybody else jumps off the cliff, would you? Oh, well, okay, well, maybe you can make this work without having the full routing table then. So, yeah, we talked them out of it, and we try and do the sparse routing table as we did before. So the connection was basically like that. The second satellite connection to Europe went out of router A, so it had 2 links on it. So first cut, we checked the paths again, 5400, 2516, 22351. 2516 was 1 hop closer, so the S-path prepend was still there, so that's all fine. But we need some refinement. 5400 always seemed to be preferred over 22351, and I could never work out why. But 5400 supported lots and lots of wonderful communities that I showed you. So I started playing around with those communities. And so I stuck some communities in there to see what happened. Made some difference, but not enough to keep these guys happy. So what I ended up doing was sending a /23 announcement out the 22351 link. And then we saw more traffic. But we didn't see the /23 everywhere. It was filtered many places. But it was obviously got enough visibility to allow some traffic for this /23 to come in over this satellite link. And actually this 23 was being used by some of the really, well, what I call critical leased line customers. They were critical as in they paid lots of money, and they were critical as in they complained a lot of the time. So we put these guys on this satellite link pretty much all by themselves, and they became quite happy because they were getting good response and so forth. So the results from that, we saw 600K on 5400, 750 on the 2516, 300 on the 22351. It fluctuated a lot. This was the pain. The traffic on each of the 3 links fluctuated a great deal. It was very, very hard to even manage it throughout the day. On a day-to-day basis, it did pretty much the same fluctuation, but through the day it changed. So I kind of left it about this, which was a kind of early afternoon thing, which was the busiest part of the network. The important point is we didn't run out of capacity in any of the links, so that was fine. But they were watching it. What about outbound? Well, we already received a default from 2516 and full routes from 5400. 22351 again can only give us the full routing table or static route. So we took the full routes from them. We discard the prefix, which had the top 5 ASs in the path. So that was the change to answer your question. We actually relied on the top 5 again because adding the other 3 actually didn't really help us very much. The 22351 configuration, we did the same thing. We discarded the top 5, and then we took 22351, their customers and their immediate neighbors. We allowed those prefixes in. Okay, and the result for that was we had about 35,000 prefixes from 5400. The routing table's grown a bit. 2,000 from 22351. We got about 200K bits per second outbound on the 2 big pipes, and 50K bits on the 22351 link. So that was sort of okay. I'd have liked to have more going out to 22351, but I couldn't. There's nothing I could do to try and make that happen. Obviously, there's some connectivity between the BT Ignite network and 22351 that just makes this not possible. But anyway, it was not bad. Outbound doesn't matter for this network. The single satellite connection to 22351 could have taken all the traffic in any case. So I didn't really worry too much. I was just trying to make sure that it looked reasonably symmetric, which is what it ended up being. And MRTG graphs, as you can see, compare 5400 with 2516, it looks pretty good. And this one here, I mean, sometimes it maxes up to almost 640K, and I've no idea why it does that. It's obviously what these particular customers on the /23 are doing. If they start downloading, Windows updates or something like that, then the link just goes boom, full up, and that's what's visible on the MRTG graph. But I was quite happy with this, and they were quite happy with it. Well, it was a good attempt at trying the load sharing. Configuration is all here in all its wonderful glory. And that's the 22351 link again. We've got an out filter, we've got the in filter, and we've got the route map. I've got the maximum prefix. Oh gosh, if it's still 120,000, we probably need to go and fix that. Oh no, it's not, because we're filtering what we receive. The maximum prefix comes last. So we're only going to hit 120,000 if the prefix list and the inbound filter list are blown away, which would take a lot to do. So the maximum prefix is very much there as a last resort. And the router's got so much memory in it anyway that it can take about 5 copies of the full routing table quite easily. And then that's the same as before. So the out filter. So here we're sending the 19 and we're sending 1/23 as well. It doesn't have global visibility, but it's got enough to give me the load sharing that I want. And there's the AS path filters we saw before. This is the one for 5400, and that's the one for the 22351 network.
So it looks like in access list 3, you're not denying the top 5 AS. I was just trying to follow along.
Yeah. I thought I did, but it must be something with the connectivity. I'm pretty sure 22351 doesn't connect. It doesn't connect immediately to those 5 ASs. So yes, I did have them in, but they didn't do anything, right? Because 5400 from memory, I'm sure connected to at least 701 or 7046, or was it 7018? I'm pretty sure they did it those days. Or at least they connected close enough to actually impinge here, which is why I had to put them higher up. Now I had it in for 22351, but they don't connect directly, so that's why I've tossed it. I'll need to check, but I'm pretty sure that's why. Okay, and the route map at the bottom, well, there are all those lovely communities I showed you that BT Ignite were using in a few slides ago. So I've decided to send all those communities. Well, I was just playing around. I guess I just left them there. But those are mostly to, what were those ones again? 2000 was to do a prepend to particular peers, and I've forgotten which peers those were, but I think they were US ISPs with a presence in Europe. That's right, they were US ISPs who landed their AS in Europe, because we wanted the US traffic to come in through Japan, not come in through Europe. That was the general model. We're trying to get European and East Coast traffic to come in through the European connection, and West Coast and Asian traffic to come in through the Japanese connection. So that helped do it for particular sites that we were looking at. I don't remember the reasons why now. It was last year. But, okay, router B, nothing's changed, same stuff. Oh, they've got new software now, so they've got the route refresh capabilities, so no soft reconfiguration. Otherwise, it's exactly the same. Okay, prior to installation of the new 640K link, ISP was complaining about both 1 meg links being saturated, and therefore they ordered a new 640K circuit. But they actually didn't check and see what the traffic was, and I did a little bit of research when I arrived using NetFlow, CFlowD, and FlowScan, and showed that good old Kazaa was to blame. Because people there had discovered Kazaa and was like, hey, yeah, great, I can download all these wonderful things that you can download with Kazaa, and run all servers and all the PCs, and the rest of the world can download things from them. And that was because it was seeing quite a lot of outbound traffic as well. Not full, but quite a lot of outbound. But basically during the day, and suspiciously enough, during the night, the inbound links were saturated. And, well, Kazaa was causing the problem. And of course, it was easy. I mean, NetFlow was switched on. We were capturing all the data. Just nobody was actually looking at it. Net set it up for showing them what you could do with flow scan and so forth, and drawing all the pretty graphs. They never looked at it. And it's like, guys, you've just gone and bought this circuit, and all it was, the problem was this file sharing thing, which you've banned by your terms and conditions anyway. So, what we did was, we blocked Kazaa during working hours, 8 a.m. to 8 p.m. So time of day access list, wow, that solved it. The circuits moved from 1 meg saturated to about what they were 2 years ago, about 600 kbits per second inbound. We didn't even need the new 640K circuit. But so that managing directors and so forth and governments don't get upset, we just said, well, we'd made some fine tuning and the usual stuff. So, but that really helped. And of course, the complaints about the net being slow reduced. I mean, it was just, we were getting phone calls every day, people complaining about, this internet thing is no good at all, I remember, and all the rest. When they dialed up internationally overseas, even to India, dialing up, said, it was much faster when I dialed to India. It's like, well, putting this in solved the problem. I'm putting this in really as an interesting aside, because a lot of ISPs don't pay much attention to what's actually flowing on the network. And it's probably a good idea to get something like CFlowD up and running on the network, even with sample net flow and the higher data rate boxes, just to find out what's happening. There could be bad stuff as well. I don't have the flow scan graph from before, unfortunately. I did save one, but I have no idea where it's gone. It was brilliant. You could see the Kazaa graph picture. It was just like almost a solid line inbound, and it was just sort of bumping up and down outbound. But afterwards, that's what it looks like. I mean, Kazaa, which is, well, the purple one, it's basically not visible. I think you can, I could spot it. You could almost spot it at 8 p.m. It just bursts in. Because what happens if Kazaa can't connect for ages, it goes to sleep for a long time, or something like that, from experimentation. So even at the 8 p.m. when we allowed it, had gone asleep, so it only really tried to wake up again. So it removed the problem for them. Of course, there's Kazaa 2 now and other stuff which use random ports, which is just another pain in the neck. But at least at the time, it solved this particular problem. Anyway, so multi-homing solution with 3 links, different bandwidths, works well. Does fluctuate during the day, probably reflecting users' browsing habits. Still don't need a full routing table. Right? The default route is good enough. Remember, default route is really the full routing table. It means that your upstream ISP knows how to get to the rest of the internet. So that's all you need from them, just the default. As long as your upstream knows how to get to the rest of the internet, that's fine. If your upstream only knows how to get to half of the internet and sends you a default originate, well, that's a bit stupid, because you get half of the internet black hole. I mention it because that has happened. But if your upstream knows how to get to the rest of the internet, sending you a default route is just fine. It's much cheaper. Simple summary, multi-homing is not hard, really. Keep it simple, keep it stupid, won't go wrong, gives you more nights to sleep, less nights trying to figure out why you broke things by changing one line. Full routing table is rarely required. As I say, you only need it if you're a transit provider. Otherwise, if you're on the edge of the net, or even coming in from the edge of the net, you really probably don't need it. Default is just as good. And this is from Sean Duran a few years ago. If customers want 120,000 prefixes, charge them money for it. All you guys, I presume you work for ISPs. Well, ISPs are into making money. Float this one to your salespeople. Get them to go sell this. Here, go buy the full routing table. Sell it to your customers, even statically connected. If you make money out of it, why not, Anyway, that is it. Thank you very much for listening. If you have any questions, you can send them to me, email. I'm Philip Smith, pfs@cisco.com. Send me email. Don't expect instant responses, because I'm going to Africa for the next week and a half. Not any negative thing about Africa, it's just I'm teaching for the next week, and I'll have very little time to do any kind of email. So, but I will try and answer all emails, any questions about this presentation. I'll get the corrections that I made to this, give it to the NANOG folks to get on the website, and also update the Cisco site as well. That is it. And finally, again, troubleshooting volunteers would be really appreciated for Chicago. Okay, thank you very much. we'll see you later.